Okay, we might as well get started. So I'm Duncan Temple-Lang. My name is there. Okay. So and I'm an associate dean over in grad studies. If you have any interesting questions or thoughts about grad studies, let me know. And also I sort of work on R, developing R and languages like that. So what we're going to do today is, well, it's advanced. Okay. So hopefully you're all familiar with R. Okay, because it's not going to be an intro, okay? But we can go anywhere you'd like to go, okay? Just ask lots of questions, okay? So I actually have, when I went to make the slides for this, or the prepares, I went to my usual directory and found I had one exactly named this, okay? So this is now Efficient R2, okay? And it's totally different. It's totally different from what I did last time, because basically it's going to be a hands-on case study. I'm very fortunate that when I was working here in the data science initiative, what used to be before the DataLab, people would come in with interesting questions. Somebody had turned out to be just a beautiful block of code that they were working on, nice, not just the right size, large enough but not too large. Okay, and they came in and they said, "I need your help to make this run, because it's going to," did a quick calculation, "it's going to use 3 million gigabytes of memory, which is going to be problematic." Okay, so that's the real thing. But what we're going to talk about now is actually how you make it go fast. Okay, so and this is a problem maybe you don't have, but it's a really useful skill to have, which is how to take somebody else's code. And that can actually be your own code 2 years later when you can't remember a thing about it, okay? But so basically, just how do you understand people's code? A lot of times people don't, and they just start rewriting everything from scratch, which is a real waste of time, because people have fixed some of the bugs, okay? So the first thing to do is just make it work, okay? And that's actually a problem too, okay? And then making it efficient, okay? So. And efficiency will never end, okay? So you have to know when to stop and move on, okay? So, and one of the things that I'm going to talk about today a bit, okay, is this thing called meta-programming, which is to actually basically say, here's my code, that is the data, and I'm going to programmatically ask it questions about itself. I'm going to find out what are the functions. I'm going to find out what are the variable names. What are the variables that are never used? When do the variables stop getting used so I can clear them? Okay, what functions use global variables and when? Okay, so you can do this by eye. You just read the code. It's very hard because you're trying to assemble. You're trying to assemble it in your mind, and as the code gets bigger and bigger, it becomes harder and harder. Whereas these tools sort of just programmatically allow you to query things. And there's about the code itself. And we do it in two different ways. One is called static analysis, where we don't run the code, we just actually analyze it and ask it questions. The other thing is called dynamic analysis or runtime analysis, where we actually just capture things as they're happening and store them so we can query them later on, like counting the number of calls to a particular function, or checking the types of the arguments or the dimensions of the arguments in each call, so we can actually build up an actual pattern about it and understand what it's going to do, okay? And what I'm going to try to do here is less technical. It'll still be technical, okay? But it's really, one of the things that I find is when you read books, they tell you how to do things, how to call this function or whatever. What's less commonly taught is what do you do next? What is the process by your thinking process as to what you have three options, which one do I take and why, and which is going to be more efficient? A lot of this is what's called experience, okay? And so it's nice if we can actually teach it faster than actually just having to wait to get it. So yell and ask questions as we go along, please. I'm actually we'll see how it works, but I'm going to get you to do a lot of the work, okay? As I was just saying to Mafani, I started working on this code a long time ago. It comes from Lauren Adams, who's a PhD student who graduated about 2 years ago, working on the optimal way to release water from reservoirs. You have warm and cold water, and it goes out of the reservoir and goes downstream, and it's needed for the environment down there, specifically for fish in this particular case, having a healthy fish stock. Okay, so you have to release it so that there's no drought. You also have to make sure that you have enough when there is drought. You also have to make sure you don't exceed the capacity of the reservoir, okay, when it rains. So it's a very delicate balance, and as to how this works. So they had a new way of doing this, and the way you do it is you basically compute the whole thing and figure out what the optimal strategy is. Okay, sounds simple. So I have a version of this, an early version of this code. Okay, so here it is. Okay, so all the slides here and some extra information are at this spot. Okay, this is a Git repository. Okay, so you can go to it on the web or just clone it would be my suggestion. Okay, and what I want you to basically do is this. There's a file called big.r. Okay, I'll just bounce my way over to here for a second. Okay, so we go down to here. It's under code. Okay, and there it is. Ignore the rest for the moment, please. Okay, so this is it. Okay, let me just go back. I needed to. Okay, so hang on a second. I should have opened that in another one. Let me just come back over to here. Okay, so basically what I want you to do is this. Okay, I want you to look at that file, and I want you to, okay, I want you to answer these questions for me. What else do you need to do to run that code? If you clone it, you can run it, okay? And you're gonna find there's a problem. You're gonna run into a problem very quickly. And then you can fix that problem, okay? And then you're gonna run into another problem, okay? And the trouble is it takes a long time to run, and then they hit a problem. So you actually want to preempt these, okay? So basically what I want you to do is look at that file and tell me what you would like to know about it. Okay, you can talk to your neighbor, okay, and say, hey, what is it that I'd like to do? This is a reasonably common situation for me. Somebody walks in with code, or more to the point, sends me an email, say, hey, can you fix this? And I go, great. And I go, okay, I need a lot of extra things, and I don't want to go back one at a time and sort of say, can you give me this? Can you give me this? So what is it that I need to know? So how do you familiarize yourself with this code? If you don't know, ask. Don't read my slides. This is much more fun to some extent. Okay, we're going to do this in a compressed time, but it is the interesting part is actually the thought process rather than knowing the answer. Okay. Is anyone having any problems getting the files? Sure, thank you. Good idea. You know, it's funny. It's easy to poke. It's actually perfectly sensible code. And it's really not, makes perfect sense. And yet there's just some things that you go, don't ever do that again. And which is always good. Just write it so it works and then fix it later on. But when you run into, okay, we need 3 million gigabytes, it's like, okay, we're gonna have to rewrite this quickly. In what sense? And yet there's a huge amount of comments in there as well. So it's actually structured in blocks. So, and so it's there. It's, and some of it is highly, oh, thanks. Welcome. What are you guys thinking? What else do you need to run this code?
I'm just looking at the setwd command and wondering if the data is being repository.
So the trouble is there's a setwd, so set working directory, so that, and it's got somebody else's name. It's not going to work. It's never going to work on my machine. Okay, so that's fine. And then we don't actually, you said it is the data there. I mean, we don't even know if there's data involved in this. It could be in my world, it could be just a pure simulation with no data. Okay, and which would be bad, but there are data files that are needed here. Which ones? Okay, so you need climate. So how many files do we need? How many data files do we need? So the trouble is, if you start running this, it's, some of these data files could be huge, and you go through and you run it, and it takes an hour, and then you get an error because it can't find the next file. And then you mail the person, can you send me that file? And they say, sure. And they go, they know full well that you need 3 files, but we can do this slowly. So one of the things we actually want to do is we want to sweep through and actually find where all the files are mentioned. Okay, that's hard. How do you do that?
So you want to read that CSV?
What if it's not a CSV file? What if they use read.table with sep equals, a comma, so they take over? Or if they read an Excel file, so the read Excel function. Yeah, so we kind of need a list of functions that could read file, that are likely to. And then how would we find them?
Find the files?
How would we find the calls to those functions? And then once we've done that, we've got to look in at the arguments and find the file. It's trivial for you to do until I give you 100 of these scripts, and you go, I'm tired. Okay, you'll see if you look in the directory, you'll see there's another file called toy.r. That I was given 2 files, big and toy. Okay, toy runs. No, it doesn't, because you don't have the data files, and because it's got all the setwd commands on it. But one of the other problems I have to do is I have to figure out, are they the same file, essentially, or what is the difference between them? Now that one turns out to be quite easy. They're almost identical, almost. There's only 3 places that are different. But again, we want to actually get the differences semantically as to what the actual meanings of the differences are, as opposed to just text comparisons. So if you want, go through, just take this file, open it up in your text editor, okay, or just in your web browser and search for read.csv. Have you done that? How many files do we need? 3, okay? So we run into a problem that, first of all, you have to be manually doing this and typing, which is fine. You got to be there, but it doesn't scale, okay? That also wouldn't work if one of those, that would give you an error, or a false positive, if one of those calls to read.csv was in a comment. Okay, or if it was inside an if false statement, which I do all the time. I say, this is code I may want to come back to, but I don't want it to run when I source this file. So what we actually need to do is, so you're just doing it with the text editor and sort of run search patterns is not going to do it, because you're going to get false positives. You're going to miss things where it's actually read.table or some other function. So you're going to have to build up these functions. But that one's something we'll actually deal with. So how would you do this? How would you find all of those calls to read.csv in R programmatically? And by the way, there's pardon? Excellent, good. So that means you have to wait a year. No, so the other thing is, so somebody mentioned setwd. Okay, so first of all, this is just a bad idea in any script if you ever want it to run on another machine. That means if you want to give it to me, I have to go in and change all these things, and it gets tedious. I have this thing. I'm actually very happy to look at people's code and help them, but the trouble is, if I have 10 minutes to help them and it takes me 10 minutes to actually get it to run, that's done. I don't have any time. So you kind of want to maximize the portability, so you can give it to somebody else. They're more likely to help you fix and debug your code or whatever. So we look for, there's another really, really nasty thing that people do, and it's at the top of the file. So I'll download your file, attach it from my email, okay? And then I will source it in to my R session, which I'm busy working in, having computed massive amounts of data, and you just wipe it out clean, okay? So first of all, how would we fix that?
Run it in a completely new R environment.
I can't do that. I only like to have one window open. No, I don't. That's not true. If you see my computer, I have billions of windows. So one of the ways we can actually do it is just run it in a separate R session. That's absolutely fine. Okay. But actually, one other way we can do it is this: is we're going to do source. Okay. You know. And so you're going to source big.r. Okay. And what I'm actually going to do is this. Okay, have you seen that before? Yeah, it's kind of nice. It's very handy. Okay, so you've seen source. I hope you've seen source before. Okay, that just says just read the code from that file and evaluate it line by line or expression by expression. What source does is it actually parses the file and then evaluates the expressions, which we'll use later on too. This thing here, it creates a new environment. Okay. And by the way, when we organize these workshops, I'm going to do 3 workshops on R fundamentals, which is how you understand how R works and so how to reason about it. We should have done this. We should have done that first and then this one. But I agreed to do this one. So then we didn't want to change the schedule. So what this actually does is it says evaluate all of the commands in here, but inside in this environment. Okay, and the way we construct this environment that we'll talk about this in the R fundamentals, that new environment can look along the R search path, but it won't actually, and it can see the global environment, but it won't write into the global environment. So we're going to actually have, here's E, it's a box where we put variables, and then it's going to have the global environment and then the search path elements. So all the evaluations will go in here. Nothing will happen. This will remove everything in my empty environment, and this is good. But this is very bad news. Just don't do that, okay? What you really want to do is actually, if you want to be polite, you want to remove you know, there's a variable called best. There's another one called all stages. By the way, I know this code like the back of my hand now. I've been working on it far too long. So what you actually want to do is you want to go find all of the top level variables that are created in the script and then just remove those and those alone. Okay, that's the right way to do this. Is don't clean up everything, clean up your own mess. Yep. Top level variables. Okay, so let's take a look over here. So that's the question: is what variables are there here? So this is comment. Here we go. Okay, this is a top level variable, month list, because it's if I source this in this and run this in the global environment or in my own environment, it will execute this command, remove everything. Then it will change the working directory, which it will fail, and I'm done already. Okay. They will create mround, and that's a function that'll land in the environment in which I'm evaluating this or sourcing this code. So that'll be a top level variable, mround. In the environment E, or whichever environment I'm running it in. So if I don't do this, if I just source it, it'll go straight into the global environment. Yeah, if top level for this script, yes, is what I mean. So what I'm saying relative to the source, where's it going? What variables are going to get constructed? Okay, so it's not going to construct. We'll construct all of these guys, but it won't create VC options and VW options because they're inside a function. Okay, so but this will be a top level variable. Okay, so what I actually want to do is I want to go through and find. Okay, I want to remove this. So I'll comment this out. But I have to find it first. And, you know, it's just amazing. As the script gets longer and longer, you'll find it in the middle. As you know, and that's like, oh. And again, I don't want to find these if they're commented out or inside. As I say, just to be clear, I use this a lot. Okay, and then I have all this code, and I want to ignore that code. Okay. So that one day I did actually do this, but then we decided not to put it into R. In other languages, you can do this, multi-line comments. okay? And it's just so easy to do it in Emacs or any a text editor just to put the comments right down. But it's kind of annoying, but there's no way of doing this in R. So, okay, so to comment out a bunch of lines and not have them as comment lines, is you can just actually sort of say plot, you know, X comma Y here, but I actually don't want to do this right now, but I want to leave it around as a segment of code that I can't figure out where else to put it because I won't remember where I put it. And it sort of makes sense here, but I don't want to execute it right now. So we just say if false, well, that's always going to be not true. So this code will never run. Okay. And then I go into my text editor, lift that code up and then run it. Okay. You know, manually, I just send it over to my R session. Does that make sense?
If false is never going to be true,
then just this code will never get run, but it will parse. So it had better be correct. I mean, if it's got missing parentheses, poor R will take the rest of your code.
Is there any circumstance where you could accidentally make that code true?
Yeah, I mean, not accidentally. You could change this to. Well, there's okay, and then I'll get on my hobby horse. Okay, there. That's what people do. Oh, it's too much trouble to write out ALSE. Okay, so they put in F, and then somebody comes along and actually earlier on in the script, F gets a non-zero value, and you're in trouble. Okay, and the trouble is, you know, F is a good one for, you know, Fahrenheit, or or an F test, and an F test has to be positive, so it's never going to be zero. So so don't do this. But you know, and you are actually spelling it out. As I say, it's what it is it's a form of a multi-line comment. That's all. That's what the goal is. Okay, everyone with me? So, who knew about sourcing into an environment? Okay, great, you did. Okay, one person. Okay, I'm gonna have to find something new, new just for you. Good. It's a handy little thing, and actually I use it a lot here because what I'm going to actually do is I'm going to source code in not this code. I'm not going to run the scripts. I'm going to source the functions in lots and lots of times. Okay, and I'm just to get their names and stuff. And I want to actually I don't want to overwrite them. I just want to actually manipulate them later on. So I want to get them in a list. And that's what I do is instead of sourcing them and putting them into the global environment, I source them into an environment and then grab them out of that. You were about to say.
If you're using RStudio, if you're using the projects, and would that also be a way to kind of isolate the scripts that you're running so they're not messing up in other work?
Yeah. What you really want to do, so what you, yes, I don't know how their projects work. I don't use them, but yeah, but it's the same, what you have is a sandbox here and you can run different R sessions, or you can actually, sometimes it's not a very big deal. Sometimes when I was working on this code, I do actually have 2 R sessions. And then I go, dang, I need data from one in the other. So I just write it to disk and back, whereas it's easier to do it this way because now they're actually in two environments. They're in the same R session. They're identical variables, and I can compare them. And that's going to be really useful because, by the way, one of the things we're going to do here is we're going to make major changes to this code. And are they going to fall? We're going to make major changes to this code. That makes me nervous because I'm not sure I'm going to get it right. So we need to test. And that means if I have the results sitting around from the original code, I can just compare them directly and see if they differ. So it's kind of nice just to have, I can have E is equal to new env and E2 is equal to new env. Okay. Another environment, I source in my changes, okay, into E2. And now I can look at E and E2 and I can compare the elements in both, okay, and see what's changed. Okay, by the way, so you've had a look at this now. Very quick look. I'm not expecting miracles here, but how fast do you think we're going to be able to make this? What's the speed up we're going to get on this code? Approximately. I mean, you can look through it. It's all in one file, okay? So we just do a bunch of stuff. I'll give you a hint. These are a bunch of functions. Blah, 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 blah. Go down. Okay, then we get into a couple of loops down in here. Where are we going? Functions, 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 functions. We get down to here. Keep going. So, I mean, this is a lot to comprehend. I actually want a programmatic way to sort of say, okay, Where are the for loops? How many for loops are there? How many for loops are inside other for loops? We can do this. You can do it with searching, but I'll show you another way in a moment. Any idea about, so what you will actually see, if we get down to, where are we? We're down to here, we're down to here. There's a loop here. Okay, so that's fine. So this one here, there's two loops. This is a function. So assuming this is going to get called more than once. Then we get down to here, and then we actually are into, that's basically defining all the functions. Makes perfect sense. You define all the functions first, and then you get into the script. Okay, and now we get into, there's a loop here. Okay, and people say loops are bad. They're not bad. It's just, they're just a lot of computation. When somebody walks in and says, "Can you make this go faster?" When do you stop, and when do you say, "No, I can't"? Yes, I can. I could spend the rest of my life making it go faster. How much speed are we going to get on this? Why? You need them. You actually need them. I could work really, really hard and get rid of some of the for loops, but these ones I can't actually get rid of. And I have to do some careful analysis because to check this. One iteration depends on the previous iteration. So we're dead in the water there and trying to actually get rid of the loops for that guy. Because what you're doing is you're going through different stages, and what happens in one stage impacts the next stage because the water in the dam, it depends on what happened previously. Actually, we're going backwards, I think. So it's kind of, okay, so when I started working on this.
So I was going to say, the loops are over matrices, so maybe if you can make the matrices sparse, you could speed that.
Maybe, except for we're still going to need the loops, but maybe, because maybe we could loop over a smaller number of elements. Okay, that's a good one to actually stick in the background. We're looping, if you look over these things, we're looping from 1 through n row, 1 through n columns, or whatever it is. Well, let's see if we can loop over fewer things. We have general strategy. Yeah.
Are they defining the objects that we're still feeding information generation?
Are they pre-allocating those? Is that there? Yeah, we'll look at that. Pre-allocation is absolutely essential. If you concatenate onto things, it just dies in any language whatsoever, where you just keep on adding one element to the end of a vector and growing that vector by one item each time. You're dead in the water. Okay, so it'll get exponentially slower, and it doesn't matter if you're only doing 5 things, but when you're doing 5 million things, it starts getting there. So when I started looking at this, I made it about 12 times faster. Okay, this is about 2 years ago. Okay, and I stopped. Then I picked it up again just before Christmas, and I tried to redo what I did, and I got to a factor of 8. And I'm going like, what do I do next? Hang on, I had notes, and I go, I can get to 12. How did I get the extra factor of 4? And then I got a little bit more, then I got a little bit more, then I got a little bit more. So what actually happened at the end of this, and I really squeezed this thing to death, okay? I mean, I'm still going, because it's just, you know. So what I actually got was a factor of, and it's highly variable in runtime, okay? Not the final version it runs pretty quickly with a little bit of variability. As a percentage, still too much. Okay, the first one took me, the original run on the toy.r takes about 10 minutes, okay? What we got down to, and that oscillates between basically 500 seconds to 660 seconds. It's is about the variability. So when you actually look at this, we get a speed up of about 500, okay, by making major changes to what we're actually doing. And there's still more we could actually do. But I did not know we were going to get to that, okay? That's the experience. I have a lot of experience in this, I don't mind saying, just because I'm old, okay? And it's like, wow, I didn't expect to get that much. And I almost gave up halfway through that sort of stuff. So it's really, really hard to know. There's some telltale signs, but they're not actually necessarily there. So they're clear. So what do we need to do? We need to find the setwd commands, because that's also not good, because you just can't move into other directories that don't exist. That means what we should actually have, so what we're going to have to do is we're going to have to go through those setwds, essentially remove them, and then find out where the data would have been relative to them, and then ask for that data. Okay, we may need to actually send an email back that says we need 30 files, okay, and they are here, 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 and here. You know, that's not necessarily the best organization for their own code, but that's how they did it, and no, I'm not complaining at all, because that was expedient for the person writing this code. So we want to programmatically go through, find those set WD calls, and then sort of take the absolute value and then the absolute path name, and then tag that on to any calls to read.csv, okay, and get rid of them. So that's fine. So we'll do that. What else will we do? Okay, so one of the things, let's just go over here and do this. There's a variety of different things. We can go in so many different ways here, but where am I? Let me go over to the code. Okay, get rid of this. So this is what I'm going to do. Okay, so I am going to do the following. Who's ever done this? No one. Okay, so instead of sourcing this, because by the way, sourcing is just going to die. Okay, even if the set WDs weren't there and everything was fine, this would basically, if I run the big one, big.r, it'll just die. It will just say I've run out of memory, and we're done. So, but what I'm going to do is this. Okay, just okay. So this is the beginning of our meta programming. Okay. So what I'm actually going to do now is this is weird, okay? So let's look at P of 1. That is the command that will get evaluated when I source, but it's not being called, it's not being evaluated yet, okay? It's just sitting there as something, okay? Let's take a look at number 2. That's the set WD, okay? I happen to know that because that's fine. But let's do the following. Let's do sapply of P, and let's just say the class of this, and we'll just look for, well, actually, let's just do this, okay? Is.call. Okay? Very, very, very quick, okay? Just runs through. The P is essentially a list, okay, of all of the commands, the top level commands. And what I've done is I just said, which of them are calls to a function, okay? 195 of them, okay, out of 195. If you come to my R fundamentals workshop, I'll tell you everything in R is a call, okay? It's just, this is the way R works, and it makes it incredibly uniform and simple to understand. So when you look at something like if, that's actually a call, okay? This is a function. If is a function you could change, but x plus y, that's a function call to that, okay? So R just twists it around and says that's the call you actually meant. That's the syntax. So that doesn't really get us very far, but let's just do the following with this, which is, let's do sapply over P, and we'll basically say, it's a function of x. I'll save this script, by the way, if you want to work through. So each of this is going to be one of my commands. X is going to be a command, and let's just do the following: is.call of x. We know that to be true, and x of 1. Well, I'm just going to show you this. Okay, x2. X2 is that guy. XP. P of that guy. What is this? What do you think this is going to be? What's the first element of this thing? The command or the function name. Okay, okay. So it's set WD, and we always do this. What is the class? If you don't know what you're doing with, what's the class of this thing? Okay, it's a class name. It's a variable. Okay, it's not a string. It's not a literal string. It's a name because it's a symbolic reference to a function. Okay, a variable that R has to look up. It hasn't looked it up yet. It's fine. But I can now go through and find all the set WDs. Okay, so sapply over P, and basically we're just going to say it's a function of x, and we basically x1 equals set WD. We'll W that guy, table of W. Hopefully this works. We got 5 calls to set WD. Everyone happy? Okay, so this is meta programming. Okay, hey, go find me all the calls to set WD at the top level. Okay, that aren't an assignment or anything like that, but that's fine. Okay, so this is much simpler. So did anyone know how many set WDs there were? Okay, no, because it's just too big text. It's like your brain doesn't need to read this stuff. Okay, and they're hidden. So now if we actually take a look at P of W, there we go. This is annoying, but we'll just do this. Oh, I can't type today. Okay, so now this is what we actually have. So we can now say, okay, can you get me the data from these directories? Okay, and now if I actually go over and say, let me do this, which is, let me go around and look through the P's where we're basically going to say, we're going to use the following. We're going to say class of X equals, okay? That's weird. By the way, I suspect nobody's seen this stuff before because it's just not, we don't talk about it, but it is so powerful, okay? So you have to need to know your way around this a little bit, and we have tools and higher level tools. I'm showing you the bare bones here at the moment. But basically I'm sort of saying, okay, go look through and find the ones whose class actually is the equal sign. Lauren, who wrote this code, uses X equals 1 or X equals some value, whereas most other people use less than minus. I actually use the equal sign, so this makes me happy. I don't have to think. But if sometimes we switch and do both, in which case I'd say if the class was either equals or the less than minus, that's the assignment we want, but we don't have to worry about that. And we're going to basically do the following now. So there must be, again, let me just do this. So let me take a look at P of 4. Okay, so she does actually use the less than minus in this one. Okay, let's just take a look at this. Okay, just while we're yeah, we could just, well, I'll pick a not quite random one, but I'll pick something like this. Okay, so that is another simple thing. Remember, this is a call. Okay, so let's take a look at P of 10. I'm going to set this equal to E. Okay, so what's E of 1? Is E1. What's the first element of E? So E is this expression. So what's the length of E? Should type. What's the length of E? It's 3. What's the class of E? It's that equal sign. Okay, what's the type of E? Language. Now, nobody's seen that one. It's like, well, okay, because you just don't come across these things, but they're very useful, I hope. That's what I'm trying to convince you of. This is super useful too, actually. And it's advanced programming, okay? I'm not saying this, but it can save you a bunch of time, okay? And I'm showing you how some of the tools we build that you can use directly, so you don't need to know about these, but that's it. So what's E of 1? It was fun what you were about to ask. Okay. What do you think it is? Remember, when we had the set WD, the first element was set WD, and the second element actually was going to be the string, the first argument. So what's this? What's E1 going to give us? It's just going to be the function, because it's going to turn everything backwards. It just says X equals Y, means that's a call to equals with 2 arguments, X and Y. Okay, so this is just that. And the second element is going to be the variable name that we're assigning to, and the third element is going to be the value. Okay, so now we're actually almost ready we go through these guys, and I'm going to look for the read.csv calls. Okay, so I'm going to say it has to be an equal sign, because if you're just calling read.csv and not assigning it to anything, we're going to get rid of that's just a waste of time. Okay, that's just like, that's nice, now move on and forget what we did. So we're going to assume they're assigning a value. So we're looking for an equal sign, and then we're going to look at the third argument, because it's going to be the right hand side. This is always the annoying part, which is it's an equal sign, so I need the second. I need the second argument. Well, but the first element is the equal sign, so you have to remember that. So we basically do this, and X of 3. Okay, now we got to think. Okay, and hopefully this is reasonably straight. Hopefully this isn't mind blowing. Okay, and this is followable. Okay, the right-hand side is going to be a call to read.csv. That's what I'm looking for. Okay, so that's just a call. And the first element is going to be read.csv, and then we have extra arguments. So I've got the expression, which is the equal sign. Okay, so I look at the third argument, which is the right-hand side, and then I look at its first element. Okay, I really should check to see if it's a call, because it could break, because if it's not a call, and I start looking at it, so I'm basically going to say, and is dot call of that guy, and X of 3 of 1 equals read.csv. Everyone with me? This is weird. This is horrible, ucky stuff. Okay, but it's powerful. Okay, so let's go say W on that guy. Let's see, table of W. Whew, got 3. Hey, Mr. already told us that we had 3, but I can now verify it. Okay, I haven't actually tested to see if they're inside an if false. Okay, but I can do that if I wanted to, because I would actually just, I can look for those top level expressions that are if false. Yep.
Okay. How, when you created the parse object P,
Yep. By the way.
what is, yes, typing structure of P is pretty useless for like, you know, like getting an over like 1,000-foot view of what P looks like or how it's organized. So how do you know how P is organized? Like how did you already know that the first was the function column, the second was going to be the variable name, the third was going to be the value?
Years of experience. How do you know? You can read the manual. Okay, Hadley has a book, Advanced R, that talks about it. It is spoken about in several books, but not much. And but yeah, and so you do actually have to know. Now, if you go to the end of my slides, you'll see that I list a couple of packages. So yeah, so we've written a bunch of code analysis tools that actually hide some of this from you. And Nick Ewell, my grad student, has written an R package that gives a different representation and a more useful representation than this, but with exactly the same concepts underneath. So it's just confusing. But this is why I'm writing this 200-page chapter, is because so yesterday we split it. It's smaller. Okay, and it's going to be one chapter on here's how you actually think about these tools, because very few people talk about them, unfortunately.
I just mean the difference between parsing a function versus parsing a structure. Like how did you know like that structure of the parsed object changes from one parse?
Yeah. So if I take a look at this, let's what was it? It was where did we see the round? Was it 4? Think, yeah, okay. So see, this is the nice thing about this is, and you just have to know how this works, unfortunately. As I say, Nick's package actually makes it a little saner, a little more consistent, and also you can do different things with it. But see, this one here is simply an expression. It's a call to this function. This is the first argument, and this is the second argument. This function is not a function. Okay, it will be a function, but it's not a function because I haven't evaluated it yet. Okay, but if I take a look at this and I look at P3, that is the function. Okay, and now if I say what is the class of that? Anyone guess what the class is? This is likely. I told you this is meta programming. It's very meta. Okay, it's like, oh, we haven't run this code. We haven't evaluated this code. We've just parsed it, what's called lexical. Like we have a lexical representation. Okay, so what do you think this is going to be? Expression? Language? It is a language object, so it'll only come back with one class here. Anyone want any other bets? Name? It's this thing that we're looking at. So what's the class? It's a call. I told you the answer to everything is a call. Okay, okay. So it's a call because it's a call to function. Okay, and so just for fun. Okay, so so first of all, let's just do this. Okay, we grab this object. Okay, I'm going to call this is F. Okay, so if I say F of, it takes 2 arguments. Okay, so let's put in 10 and 2. Okay, and it goes, what the heck are you talking about? Okay, but now let's just do this. Okay, no problem. Okay, here F is just sitting there waiting to become a function. It's got all the bits needed to be evaluated that will turn it into a function. So I call eval. And it actually evaluates that thing, gives me back the function object, and I assign that to something else. Okay, everyone happy? If you wanted to actually take a look at this guy, though, let's take a look at F. What is so now we get into 2 things. It's a call. So what's F of 1? Remember, F is my just that guy, unevaluated. So what's this look like? That's the call. What's the second argument? Okay, this is not interesting to us. Because it's okay now. If you ask me what that is, you're gonna we don't want. I'm not going to let you know what that is. Okay, okay. But what we actually want to do is this. Let's look at F2. It looks almost exactly the same as F, Okay, except for this one is this F2. This one is an actual function. Now, so again, going through with this meta-programming thing, okay? Because I'm gonna do a lot of this later on the functions, not on the text or not on the lexical parsed objects. I'm actually going to want to process these functions. So let's just take that one. Okay, what are the formal arguments of F2? Okay, they are X and base. This is a list. I know the names of the arguments. The values of the arguments are actually the default values, okay, as expressions. Okay, and now if I say, what's the body of F2? That is the code. Okay, okay, what's the class of this? Again, there's only one answer. No. Okay, it's actually curly brace. Okay, and that's just a block of code. Okay, a set of expressions. Okay, and now we're back into the parsed objects. Essentially, we've actually got these things. So we had a script, and we were looking at the parsed objects. When we get the body, we can look at each expression in the body. Okay, this is essentially just it's a list. Okay, what's the first element? Okay, it's just like the equal sign. It's the curly brace itself. What's the second element? Okay, it's the command. Okay, and what's this? It's a call. It's a call to start to multiply. It's got two arguments: base, which is just a name, and the second argument is a call to round, with one argument, which is another call to slash with x and base. We would find x and base in the call of this function, but for now we don't have a call. We're analyzing it statically. Okay, everyone happy? So we're going to be able to play with that on real functions. Okay, so we found the set WDs. We found the read.csvs, okay, and we can pull out the names. So this is, and we could find the RN there, okay. So we can, before I run code, I can actually just go and fix all these things. And in fact, what I could actually do is something like, I could do something like this: P is equal to P minus 1. Remember what P1 was? That guy. So I'm just going to go let's get rid of that. I'm not going to change the file. I'm just going to actually, I've parsed this. Okay, now I've just thrown away some of the code. So I could remove the set WDs. I could rewrite the read.csv files, calls, okay, and then without changing the code. And then all I need to do is this. Okay, or lapply of P eval, okay, and off I go. And if I want, because I don't want to ruin things, I can say E equals new.env. And then I say, please evaluate everything in there, not in my workspace. Okay? Everyone happy? Yes.
What if the data files are not CSV or send at the start?
So we want to be a little bit more general. So what we actually want is to we want code that actually says, okay, well, what if they're Excel files? So what we would do, unfortunately, so we have two ways of doing this. One of them is you just have a list of names of functions that read files. Okay, so read.table, read.csv, scan, so forth. And we would just look for any call to those. So we'd have we would have a list of known functions that we'd be looking for. Okay. The other trick is, how would we know what if I wrote another function that says my read data that calls read.csv? So sorry, do you see what I'm saying? So if I'm not making sense, just yell. Okay. So so you're basically saying, what if there was a fixed width format file, let's say, okay? So or some DAT file or an XLS. Well, there's a couple of things we can actually do. And again, we're going to use heuristics. One of them is we could look for any string, okay, any literal character string that has these at the end, and just guess that they are the names of the external files. Okay, how would we do that? We would, by the way, what we actually have, what P is, when I parse P, it's a list and all that sort of stuff. We think of it as being what's called an abstract syntax tree, okay? And what we actually have here, so when we have something like mround gets function of x and base, and then the code here, this turns into, Okay, that's the assignment. This is the left-hand side. This is the right-hand side. Okay, and then this has a body, and then this has, and it has two arguments, x and base, and then it has the curly brace, and underneath this, we actually have the code, which turns out, as you know, if we take a look at that code, wherever it was, it turned out to be, there was a star call here with, so it was x, and then round of a call to round with two arguments, with one argument, which was x divided by base. Okay, and this is a tree. So all we're doing here is walking this tree and finding the pieces that we want. So what we could do over here is we just start at the top of the file, I mean, not the file, but the parsed file, the tree, and walk each expression and walk and recursively go through all of those and find any file, any string that has, you know, foo.xlsx, and we look for this, we look at every string, okay, and we say if it matches, the extension, that's an external file, okay? We could do that. Alternatively, what we can do is we can just say, okay, I am looking for every call. So this is all strings with an extension. The extension that's in this set of XLSX, CSV, blah, blah, blah. That's one heuristic. The other one is calls to functions in read.csv, read.table, scan, you know, so we know about all of these, so we just enumerate them all. Okay, and now what I'm saying is this will fail. So these are heuristics. We're just basically going, okay, well, this is the best I can do. Now, but then somebody comes along, Lauren comes along and writes my read CSV, okay, which is just a wrapper around read.csv. But that's not in our list. So we could add it to the list. If we had a function to do this, we just say, hey, you're allowed to tell us what the names of the known functions are. But another thing we can actually do is this. We could look through every function in her script, find this, read its body, and find there is a call to read.csv. Okay, we can analyze the function to see that it itself calls read.csv, therefore it must be something that reads data files, so therefore it goes in here too. Okay, we just programmatically read the function definitions. So we can do that for all 14,000 R packages, okay? You can't do it manually. You just can't. Okay, whereas if you have tools that will actually be able to go and find it, it's no big deal. And of course, in our function F2, one of the things you can actually do is very simple. Code tools, find globals of F2, false. Here are the functions it calls. Okay? So you can now find out what functions are called by another function, potentially called. If there's an if statement or whatever it is, it may not get there, but you have this thing. Okay, everyone happy? Anyone happy? So what it's doing is it's actually, so this is built into R. Okay, code tools come with every installation of R. What it does is it goes, find globals goes in and uses this sort of meta programming to look through all the expressions in the body of a function and in the default values for the arguments, and it says which functions are called, and it gives us back a list of the functions. Because if you remember F2, so I told you that so this is a simple function. It calls star. There it is, star. It calls base, but that's not a call. That's just a variable name. So that's fine. But it does call round, and it does call slash. We have those two. We have this, and for some reason we get curly brace. Whoever wants to call curly brace, it's like, oh, I just want to group things together with a curly brace. Okay, so so this is irrelevant, and also it says there's no global variables. Okay, that's good to know. Okay, because some of these functions do have. Okay, everyone happy? Yep.
The difference between P and P
-1.
Yeah, when I did all equal on it, so it's different by like one string mismatch.
P.
Yeah, the original P, so P equals parse.
No, thank you. I'm just right. P is equal to parse of toy.r. Okay, that's that guy. And then P1, let's just say
Yeah, equals P
-1.
minus one, yeah. All equal P.
This is another thing we like. Okay, P and P1. Okay,
What is that?
so this says that those two things are not the same. All.equal is a very handy function that says, and we're going to use it. Hopefully we'll get there. What I was doing when I was working on this is I would make changes to the code, run it, and then check the results were the same with identical, and they weren't identical. It's like, oh, they are identical. They're just not identical. Okay, they're the same except for the one has names and the other one doesn't have names. But I'm only interested in the values being the same. Okay, and not the whole structure being the same. Okay, so identical is it says these two objects are identical in every respect. All.equal says, yeah, there's a little bit of fluff, there's a little bit of wiggle room we can have, okay? But this says they're not equal, and it gives a string back that says they are different in these following ways. They don't have the same length. Well, we knew that, we just took one out. I don't know why you were thinking they were all the same.
No, I was just trying to figure out exactly what changed.
Okay, and so one is missing, okay? And then we do actually have this weird thing. What's the class of P? What's the class of P? That one, okay, is weird. Okay, what's the class of P1? Okay, it's still an expression. These are very odd. If you'll notice that what I actually did was as.list of P, of W. Okay, if I don't do the as.list, it's weird. Okay, it just treats it as an expression with 3 elements. I just want the 3 elements. Okay, so we're into a very weird world here. Okay, but what's different is we just drop the first one, and then they have different attributes and so forth. Okay, because I'm not sure if they have names or not. Okay, everyone happy? So again, this to me is that not enough people talk about it. It's actually very straightforward. I know I genuinely know that that's a stupid thing for me to say. It's easy for me because I've been doing it for years. But it is not rocket science. Okay, and there's higher level functionality to do similar stuff, but you can build on it yourself, where you can actually just walk through and analyze code. So as I was saying, if we could look at somebody's function and then we realize it called one of these things and then just add it to the list. This is very handy, okay? And all we got to do, in this case, we don't have to do very much. We just call code tools, find globals, and see if read.csv or any of these functions is in there. Okay, so what else would you do with this code? So we're gonna remove the setwd. We're gonna comment out the RM. We now have found the setwd, so we know where to comment them out. We know how many there are, so even if we're going to go in and change the code, we know how many to go through, and because we found in R, we found 3 calls to setwd. We technically know where they are in position, but not in the file because there's comments and all that sort of stuff. But we can go back. We can also get the names of the CSV files, send the email back and say, give me these 3 files, okay? If they say, oh, I don't know where they are, you can like, well, we do. We know where, we can figure out because you set WD all over the place and we can glue that information back again. So let's just assume we're going to fix all that. Okay, what else would you do with this code? Given that we're going, so we now can basically run it. We have the CSV files. I gave you the 3 CSV files. Okay, so you could run it. Okay, and that would be fine. But we're going to actually also modify it. Okay. And by the way, has anyone got the 2 files, big.r and toy.r? What's the difference? That's it. And there's a third one which actually has the same value, but written in a symbolic way differently. Yeah. So in fact, actually, these are almost identical. And a simple diff will do that. But if somebody gives you 2 files and they're actually similar but not, things have been moved around, some bits have been dropped out, then you're going to actually want to sort of parse it and actually compare them and see if you can match them up or something like that. Here, the diff is very simple, but there's a problem with this. So I think because there's so few changes, what I'm going to do is I'm going to just take big out of here, throw it away, and just remember that these 2 variables get changed, and that's fine. I want to run the small version because I don't want to be sitting there waiting for days for it to fail, and so I may even want to run one that's even shorter because it takes 10 minutes to run. But I'm going to make a bunch of changes to the functions in there, And it's going to be a lot easier for me if I take those functions out of the script, because I'm going to want to test them independently of the script, because this script takes 10 minutes to run. I can't afford to make one change to one little function and then just run it again to see if see does it still work, give me the same answer. I'd like to be able to test them independently of the script. And secondly of all, if I have those two files, they've got exactly the same functions. So I've made a copy of these functions. So if I change them in one place, I can't reuse them. If I change them inline in toy, I can't use them in big. So if the big.r script has more changes to it, I'm in trouble. So all I'm trying to say here is that we have a script. We have a script, toy.r, with function, variables, variables here, some variables here. These are functions, okay? I want those functions. I want all of those functions in a file, and I'm going to name it, because I'm so creative, functions, okay? Functions.r. I'm going to take all those functions out, and then if I have another script, script 2 or big or whatever it is, they can source in those functions. I can source them independently of the script, and I can test them independently, okay? I don't have to run the entire script. So I need to grab all of those functions. Anyone tell me how many functions there are in there? 45. Okay, I happen to know this. How do I know? Because I now have to go through manually and actually move these over here, and I need to get them all. So I need, at the end, I want to verify that I got them all. But there's not 45, there's 30. There's 15 that aren't functions, but they are, okay? Okay, so again, I actually do this, and it's overkill, but not really. I don't like spending 20 minutes doing something manually and then have to go through and do it again, okay? Or there's an error in it and I don't notice. So I like to be able to verify what I've done is correct, or I want to be able to programmatically manipulate it myself. In this case, I'm not going to take I could drop the functions out programmatically like we did with p-1, but I don't want to do this. I'm going to manually transfer them from file to file, but I need to know how many there are. I need to know what their names are. So I'm just going to parse this code and find all those functions. Okay, so I'm gonna parse the file, and we just did it. We find one for which on the right hand side of the equal sign there is a call to the thing called function, and then I'll find the name on the left hand side. And then when you get into this, so if we take a look at this, final, okay. Hey, we're starting to look at the code. Anyone knows what that function does? Anyone seen this function before in your life? Good, don't. Okay, forget about it. Just don't use it. It's a convenient function, and it's going to be the bane of our existence. This is why it's so slow, this code. Okay, okay. But the funny thing is, if I'm looking for here, I said I'm going to find all expressions, programmatically find all expressions that is basically a call to equals, where the left-hand side is a variable name and the right-hand side is a call. Not yet a function, but a call to function. Then I can find these names. I will not find this, but this is actually a function now. And because vectorize takes a function and returns a function. So I have to find those as well. That's easy, because we can find all calls like this. We can also find all calls that are just calls to vectorize, because we have the tools. And we just write all the code I was just writing now. We were pulling these things apart. Once you get the fact that these are all calls and you get the basic structure of an expression or a language object, you can do what the heck you like with it. You can do an awful lot of good things. You can even modify the code. I could transform this code and then run it, and I'm going to do that later on. Okay, we're not just querying these objects. We're actually able to change them. Okay, so I need to find those vectorizers. There's 15 of these calls to vectorize, and so I'm going to have to manually move those over as well. So I've done that for you. Okay. Okay, because that just takes time. It's boring. Okay, so but this is how we do it. We run through and we find these functions. Okay, now I know how many there are. Then I move them over to another file. I take them out of here. Then what I do is I say E is equal to new environment, source my functions, and tell me how many objects are in my new environment. Okay, 45. Thank you. We're done. Okay, I got them all. If there's 42, and I know there's 45, I missed some when I was doing my manual intervention. Okay, So again, it's just a way of validating what I've done and ensuring that I haven't made a mistake. Actually, what I need to do is I may need to figure out, do they all have unique names? Because I could have actually cut and pasted the same one in twice, but no, that will just get overwritten because I'm sourcing. I could parse that functions file and find all that, but then I could actually have repeats. Okay, so because when I parse the functions file, I'm not actually evaluating any code. I'm just looking at its structure. When I source it, that says x equals 1, and then I see another x equals 2. I only get x at the end. At 1x, not 2x's, but okay, so these are things. Yep.
I missed how you knew that there were 42 like in the original file.
45 in the original file. There was 42 in the when I manually moved them over. Here, this is how. Okay, just to be clear, okay, because as I say, we go back over here. So let's just look. S_apply over P. Please go in and for each top level expression, get me. Okay, I am looking for W. Okay, X. Here's the expression I'm looking for. Where do you go? Hang on, let me show. And you have to think about this, okay? I'm looking for an expression that is of class equals, where the left-hand side is a variable name, and the right-hand side is a call, and whose value is function. The thing we're calling is function. We got close with that earlier on. So what are we doing? We're basically saying class of X is in C of equals, and that guy. Because remember, mround uses the less than minus, just the one, okay? So it's there. So the class is in this, okay, fine. And X is dot name of X2, okay? Okay, so the second argument is a variable name. It's not, it can't be a call, or we're not putting it into a list or anything. And then I need the third guy, and is dot call of X of 3, and X of 3, 1 is equal to function. Okay, we do that. Okay, let's just see what happened. Okay, good, no error. That was good. We like that. Hang on, sorry. Okay, table of W. Didn't I say there was 30? I know this code. Okay, and now, so we got those guys. Okay, so if you really want me to, now let's do the following, which is P of W. Okay, what are their names? S_apply of P of W. Okay, I want to do the following, which is function of X as dot character, because they'll come back as names otherwise, X of 1, 2. Okay, those are the names of the functions when I evaluate them. Okay, what did I do? I just said, I found the ones I care about, and I want the left-hand side. Okay, and because the left-hand side is a variable name, we check that, and I just basically go get the left-hand side is the second argument. Sorry, the second element of the list. First one is the call to equals. Okay, so everyone happy? So they're the two pieces. And then let me just get rid of those. And then let's do the following, which is S_apply over P, where the function, okay, so we'll just, actually, let's go back over here. Let's do this. It's one of these guys again, it's this. Now, but the third one is a call, but this time it's a call to vectorize. These are my 15 other ones. Okay? Same trick over and over and over again. Okay? But it's a powerful trick. Happy? Danielle, you happy now? I'll save this. If somebody reminds me, I will say it. Okay, and then because the key thing is to sort of say, okay, you've got the basic structure. A call is just the first thing, the first element is the thing you're calling, and then blah, 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 blah. Okay? So now what we've got is basically, okay, so then you go through the arguments, and by the way, how many for loops are there at the top level? Not very hard. P, class, table. There we go. There's one assignment with a less than minus. I remember the mround, the one just makes me type more because I have to take care of that. Okay, there's 177 equals, just simple equal expressions. There's 10 calls. What the heck's a call doing there? They don't do anything. They're not assigning values anywhere. 5 of those are set WDs. They have a side effect. but the other ones are not doing anything. They're useless, okay? And the set WD we don't like anyway. And then there's 7 for loops, okay? And by the way, what's a for loop look like? Okay, so when you actually take a look at this, so let's go and say, in this case, we'll do W equals 4. We'll take a look at one of them. So these are this is another thing. So now if we look at P of 6, well, this is a nice simple one, okay? Okay, this is P of 6. Okay, so what is this? What's the length of P of 6? It's got class 4. It's a for loop, okay? It's got length 4. 4 is the first element. I is the second element. This expression, not the vector 1 through 12, but the actual expression that will yield the sequence 1, 2, 3, 4, 5 up to 12. That is number 3, and 4 is the body. The body is a curly brace, and we can go through and grab stuff. So we can programmatically manipulate these two, okay? These also. Everyone happy? Let me go back over to here where we were. Okay, so let's go do it. So we found all these things, okay? By the way, I could have done this differently. I could have actually used a package that we wrote a long time ago called Code Depends, and that's a very useful package as well, but I wanted to show you how you can manipulate the language objects yourself, but there are higher level functions. So you could just say, read the script from Code Depends, you say, read the script and then get their inputs. And this gives you a lot more information, but it'll find the files, things that it considers to be files, okay? And it uses a heuristic. The trouble is, if the heuristic doesn't work, you need to kind of augment it yourself, okay? But it found the 3 CSV files in just very simple line of code. These 2 lines of code, 2 lines, okay? It got a false positive. I don't know why it did that, okay? We'll look into that, okay? Also, you can just do something like this. This is another thing. This is the R static package, which is a little, it makes things slightly easier in some regards, as this is my grad student, Nick, who wrote this. So you can basically go in and find nodes, and it recursively goes through, and you can put in any predicate function, any function that says yes or no for what you want, and it gives you back the nodes. So you can actually do those, okay? So cleared that, okay? We can also do we can also find those, I think we'll get back to that in a second, okay? So we've got to this, okay? Okay, you've got those functions. I'm going to tell you, we're going to change those functions. They're not going to look the same at the end, okay? Those vectorized functions have to go, okay? Let me tell you, well, okay, we know what the vectorized functions are. If you actually did the manipulations like I was just doing, we could look at the names of the vectorized functions. They're always, because the way Lauren wrote this is, they're always final inflow prep gets called to vectorize, and we remove the prep name and assign it. Okay, so final inflow is equal to vectorize of final inflow prep. It turns out that she has that 15 times. Okay, so the prep is the preparation, and the version without the prep is the vectorized thing. Okay, and vectorization, by the way, if you want to make R go fast, vectorization is the key, but not vectorize. Okay, vectorize is very slow, but it's just very, very convenient for certain things. Okay, so one of the things one of the things, by the way, I have a picture of this. When I get those functions, now I got those functions in a separate file. Okay, I got 45 functions. I want to see which ones call which other ones. I want to see which ones are at the center, which ones are likely to be the workhorse, the ones that are called by every other function. So one of the things we can do is we actually build a call graph. So we just very simply, we can do it. We could do it manually now. You loop over all those functions, and you find with code tools, you say which functions do you call, and now we just build a little network. Okay, that function calls that function calls that function also, and then with iGraph or something, we just build a little call graph, and it can be very useful to see. Okay, and that's easy, and there's high-level functions to do that. So here's my problem. Okay, and this is bringing us to another part of metaprogramming, I think. Okay, I am going to take those functions, okay, the 45 functions, and I'm going to modify them, and I have to ensure that I get the same values back. So if I was writing these functions from scratch, we tell you, before you write a function, write the tests, okay? So you just write down sample inputs, and you figure out what the answer should be, and then you test. that you get that answer. And so you pass it in where you pass in a single value, another one with a vector, and another one with a vector with NAs in it, and does it do the right thing? So you start, and then can it handle a matrix? Okay, so when we're designing the function, we should be thinking about what it's going to do and build those unit tests. We are in a totally different situation here. We have no idea what the arguments look like. We know how many arguments there are to each function, but we have no idea what they should be. We can read them all, but how the heck am I going to build tests? Anyone got any plans? Because this is going to be a complete waste of time if I make this code go super fast and get exactly the wrong answer. Okay, it's a disaster. So how am I going to actually build these tests? Or am I? Or will I just go for it and just go, I'm never going to make a mistake? So how are we going to test? Anyone? Any thoughts?
The problem is you don't know what the functions are supposed to give you as outputs, right, in the first place. So how do you design a test when you don't know what the answer is supposed to be?
Yeah, and I don't know what the inputs are either. So I'm pretty much dead in the water here. I mean, I can look at the functions and I can start thinking about what I could read the functions. I could read the code that calls the functions and try to figure, oh, that seems to be passing in a matrix or whatever it is. I could figure that out, but it's a lot of work. And I don't know if I'm going to get any speed out of this. We haven't even started talking about getting this to run yet. You know, at this point I will run. I will run the toy and I will just check it works. Okay, and it takes 10 minutes and that's fine. So now I have 10 minutes of dead time where I can actually think. Okay, so I'll do that in the background. But then I'm going to say, I know what I'm going to do. I'm going to butcher this code. Okay, it's going to be, and there's going to be times when I just give up. And I go like, it's not worth the effort. So I have no idea, but I need to be able to test. And I don't want to, and again, I just don't have the time to read and understand, comprehend the code manually.
Yeah, I mean, you have something that isn't working, just needs to be set up. So you get some output from it, and you want to maintain the same output.
Okay.
So save the existing output and compare that to whatever.
So that's one approach, and that's a good approach, so what you basically do is you run the script. Let's say we do it like this: E is equal to new env, source this script into this thing. Just save E, write it to disk. That's truth. That is my gold standard of all the top level variables. So there's 177 assignments in that script. Some of those are functions, so we take out the 45 of those. We should have. Okay. So let's be bold. I only care to see the last variable. It's called best. That's the answer. I don't care. I'm only going to test this. If I get the same answer for best with my new code, everything must be right. That's just not true at all. Okay. So what I can do is and I can do that. By the way, that's what I did. Okay. I was moving quickly, so I just compared best. Why? Because I knew I was actually not making errors. Not quite. Okay, I thought hard about making some changes. Okay, and then I did. I was just describing. You know, at one point I made changes, and then I modified the change, and I introduced an error by leaving out an equal sign on a greater than or equal to, and then I started getting the wrong answer. So one of the things we can do is the following. Okay, and again, it's not obvious. It's not obvious. This is a new situation most you're in because it's not your code. Normally you're writing functions, and how many of you write tests for your functions? I won't look. Okay, liar. No, I'm just kidding. Yes, it's always helpful. So one of the things you just do is you basically just, you know, we run like this. So E is equal to new.env. By the way, I'm going to have to do this now. Source of functions. .r into E. I can do that. I have to do that first because the functions don't exist anywhere. Okay, so I always want to make sure that I'm evaluating in the right place if I'm doing this. But now E should have all of the variables. So if you take a look at our code again, we should have. Okay, what you'll see is, you know, when we get down to the end, okay, you'll see we'll have variables like P, which is actually in a loop, but it becomes a global variable, which is fine. But you'll see fs and f star value. And you'll see these. Sometimes this one and these two actually are created in here, and then they're overwritten. So I won't actually see each value of these, okay? I'll just see the last one when I do this, because they'll get overwritten when I source, okay? So I may want two things. I may want to just compare, so we can do this. We can compare best, which is the thing I'm interested in. Just, we'll go for broken, so say if that's the same, I'm happy. Or we can compare all variables, all sort of top level variables, let's say, top level variables. Hey, that's easy. We got E and E2. We just find out what names they have in common, loop over those guys and say all dot equal or identical. And if we start, whenever they're not, we go, uh-oh, and that gives it. Or what we can actually do is the following, is actually get all intermediate values. So in other words, we could see things like fs star and fs star value 1 for each of those, and then when they're redefined, capture that as well, okay, and have to call them 2 and 3 and 4. Anyone know how we do that without writing the code? Because I'm not going in and manually doing this, because I'm going to make even more mistakes when I do this. I mean, I could actually say fs1 equals fs equals vector. Nobody uses fs1, but now it's actually assigned. But let's be smarter than that. So, but these are, again, so let's figure out how we're going to do that. But this is easy. We just look at that. We run it, and we compare $E$best and E2$best. This is easy because we just compare everything that's common to both, and we just compare them. This one, we have to think about. Which one is best, by the way?
Probably all intermediate.
Yeah, because it's very possible that we end up with the right value, but for the wrong reasons earlier on. And also, we need to know where it went wrong, not at the end, because we just get information that best was wrong. Okay, good. We've only got 170 calls to go through, so that's not going to be. So this is definitely better. So we would like to be able to do this, but we don't want to change the code. Okay. By the way, there's a fourth way. None of these are actually a very good idea. They're a perfectly good idea. That's exactly what I did. This is because I was lazy. I did this. Okay. And then I went back, and because it caused me all sorts of grief later on. Okay. What you actually really want to do is you need to build tests for each individual function, because now I have to run this darn script every single time, the whole way through, to actually compare. And it takes 10 minutes, and that really is too long a turnaround time for a tiny change. So what I want to be able to do is I want to be able to call a function that, look, I change one function. I want to be able to test that one function right now and not have to do all this stuff. But I don't have any calls. I don't know how to call it so that it would. I mean, I can make up calls, but they're not representative. So I'm nothing. So how would I make up calls? Sample calls that are realistic, authentic, that actually mimic what's going to happen in the script. There's a simple way. I can capture every call to every function of every one of those 45 and store the inputs, the arguments. And when it finishes, I can get the result, and I can store them. And then whenever I make a change to that function, I can replay them. Okay, I don't know how to make calls, but somebody does. The script, the person. These are not general tests, but they're the only ones I'm interested in, because they're the ones that are actually going to be used. So what I want to do is I actually want to collect all calls. Okay. So I want their arguments. I also want the result. And if I have those, will I be able to retest? Will I be able to test these functions? And the answer is no. I'm missing one thing, or one concept. I need the global variables. I need the global variables that were in effect at the time, not later on. Okay? How do I capture those? So I got two questions for you. How do I capture all the intermediate values without changing the code? And how do I capture all these calls? And I mean all of them. Okay? Because there's no point in just picking one call for a function and then saying, oh, look, it works for that, but it doesn't work for any of the other ones when I change it. Anyone know how to do this? Fortunately enough, you don't need to know, because I wrote some code to do this. Okay, but I want to tell you how to think about doing it, because so you can adapt it for other purposes.
something about the function environment, the execution environment.
For this, which are we talking about? This one or this one?
In order to collect all the global variables.
Sure. So first of all, we can find the global variables. Okay, the code tools finds the global variables. Actually, it doesn't. Okay, it gets really, really, really close to finding the global variables, but it doesn't. It's not perfect. Okay, so we wrote another version in a package called Code Analysis that does get it more right. Okay, so but for the most part, code tools is all you need. So we know what the global variables are. When we define a function, we can immediately check to see, does it use global variables, which ones, not which functions it calls, but also which variables does it use. So we know ahead of time what globals to calculate, what globals to capture. Okay, so that's fine. So, but that's before we run. We need to capture, so it's a runtime thing. We need to capture every call. That's figuring out which globals we have is a static analysis that we do before we run the code, before we make a call. So what is it that how do we capture all the calls to a function? One very simple way, we take our 45 functions and we edit them, and we just add a line that says, you know, at the beginning of our function, so we now have mround equals function of x and base. Okay, now we just change it a little bit by actually says, okay, grab the arguments, list of x equals x, base equals base. Okay. Okay, we call this args, and then we say, okay, now give me, now do the actual computation, the regular, leave the code in there. We say answer equals that guy, this is args. Here's my answer. Now we actually combine, now we have a list with args and the answer and the globals, okay? And then we assign this into something, we'll call it mround info, gets, okay, we're gonna globally assign it into this thing, not into that thing, we have to append it to that as a list. Oh, geez Louise. Okay, this is beginning to get annoying. I gotta do this for 45 of these functions. This is getting old, okay? But that's what I want to do, isn't it? I basically want to add code that grabs the arguments before anyone touches them, before they, okay? Then I want to execute the regular code. But I can't return, I have to grab the result, okay? And then I want to collect all that together into one object, into a list, and then I want to append that to a list that collects all the calls. So when we run the script, an mround gets called 1,000 times, I will have 1,000 objects, 1,000 lists, which each of which gives me the full call. Yeah, everyone happy? How do I do it?
Override the function called function.
You don't want to go there. Because remember, these are already functions. Yeah, so no, so it's because it's not calling function, because that will happen in the evaluation. No, there's a very there's a function in R that is extraordinarily useful. Just like the language objects, nobody knows about it. Okay, few people know about it. It's called trace. You say trace in quotes or not, you know, mround. Okay, if you just do that, trace of that, every time mround gets called, you'll see something on the console that says tracing mround, and you'll see the 1,000 calls go by. Okay, so that's fine. It kind of just tells you, yeah. So it's handy, you know, you can trace a function that's in a package and sort of, I wonder how often that's called. All right, is it called at all? I'll just print out when it's called. But what we can also do is we can put in an argument here that says, we'll do something like this, okay? We'll just say counter gets, let me try to write, okay, counter less than, okay, global assignments, okay, a non-local assignment, gets counter +1, okay? We're almost there, don't do that, by the way, okay? We're missing a part, okay? What this basically says is, what I wanted to do, I'm basically saying, trace mround, and I want you to add that expression, okay, as the first thing you do. in that code. So basically, I'm gonna make it do this as well, ultimately. But this is just a simpler word to write. I just want it to do something every time it enters that function. The trouble with this is, because R is actually a sane language most of the time, what we're actually saying is trace, call trace with this argument and this expression, which means it will evaluate this as the second argument to trace, which means it just updates counter and it gives the value 1, let's say. But that's not what I want. I want it to do that expression, like to evaluate that expression inside the call frame of mround every time. So that's easy. What I actually mean here is quote that guy, okay? I say quote this expression. That means don't do it. Just treat it as a language object, please, and hold on to it, okay? So if I do something like this, quote, counter gets counter plus 1, okay? So if I do, well, let's just do it this way. This will just give me an error because there's no such thing as counter, because I haven't defined it yet. I'll say, okay, well, I better set counter equals 0, okay? That's fine. Now if I do that, I go, great, now counter is 1. Now that's not what I want. I wanted to do it when I'm in mround, thank you, not now, okay? So I set counter back equal to 0, okay? And now I do the following, which is, so I say, well, so quote of counter gets counter plus 1, okay? Quote, okay? And now I'm going to call that E. So E is one of my expressions again. It's a language object, okay? By the way, here's counter, eval E, here's counter, okay? So I have full control over R now because R basically exposes itself to how it works. We can mimic and leverage, okay? So all I now need to do is, so we have a function called F2, I believe. So let's just trace F2 with E, okay? I'm going to put in quote, counter gets counter plus 1, okay? That's fine. And now I'm just going to call mround. So remember, counter, it currently has the value 1. Okay, mround of 10 and 2. Ugh, F2, because it's not called, sorry. Okay, so now it's F2, bingo. Notice it's tracing, gives us back, it behaves exactly the way it normally does, but counter is now 2. And if I do something like replicate of F2, well, 3 times of F2 of 10 and 3, or 4, well, it doesn't make any difference. There's counter, it's 5. So it's counted every single thing, okay? And I can put in any expression I want, okay? I could put it on, I can either put in an expression like quote, or I can give it a function to call, which gets called with no arguments. So this is a way for me to inject this code in here, okay? I can just loop over these 45 functions and say trace, and build a little expression in here or whatever I want. Okay, how am I going to get the answer? Because I need the answer as well. So I can get the arguments. I can also get the global variables. Okay, because I know what they are ahead of time. Before I trace, I can calculate the global variables and say get those as well. So I got those 2 guys, and I need the result. And oh, thank goodness, somebody implemented a nice little experimental feature in trace that allows you to say, hey, first of all, very useful. Trace says, do this at the beginning of the function, whereas actually trace has an argument that says, do it at which expression in the body. By default, it's the first one, but we can say at the exit, okay? Or we can say at the fifth expression, or actually in the 5th expression in the second argument, do it there. So we can specify where it goes, but we can also say, do it at the end. When you're just about to leave the function, arrange to do it, and then we can get access to the result. Okay, and there we go. So I wrote a package for Nistar a long time ago to do a variety of things. Well, originally it just did one thing, and that's why I may change the name of the package. But all I want to do, so this is what I want to do. I actually want to calculate the number of calls to each function. Okay, because when I just don't want to waste my time making one function go very, very fast, and it's only called once. Okay, and it takes a millisecond. Okay, so there's a package called call counter, and it actually has a bunch of functions in there now, which count the number of calls, or collects all the arguments, or collects the information about the argument. Sometimes I don't want this, by the way, if you pass in, if you call mround with a 100 gigabyte matrix and it's called 10 times, you're going to capture that object each and every single time and make a copy of it, okay? And that's not going to be good. So this can get big very, very fast. So sometimes we just actually want lesser information about a function. How many times you called? What was the length of each argument you were called? Did you want to come in? Okay. Yeah. We can collect different pieces of information. Actually, what one of the first pieces of information I needed, well, first one was how many times you called. The second thing I needed was, tell me the dimensions of your arguments, okay? Because I need to know which ones are vectorized and which ones aren't, which ones are getting called with vectors. So, and in addition to which, it also does this. The package also does this. Again, it does it all through things we've seen, just trace, language objects, and so forth, okay? And what this does is actually, what it does here is it actually runs, when you say, instead of saying source this into E, you say, hey, could you, I forget what this, I think it's called, I think I called it store eval. What it says is, don't source, call my function, I'll parse this. I'll parse the script, and I will work through every expression. And every time I see an assignment, I'll create a new variable with that version. So version 1, version 2, version 3, and then we'll be able to replay the entire thing. Again, it's just call to eval. So we can build that without knowing, we can build that entirely on top of our code. We don't need to hack R itself. Okay, so we can collect all these arguments, and then we can actually replay them. So there's another function in this thing called test fun calls, and you basically give it this list, mround info or something, wherever you collected everything, it has a big long, all the calls, and you give it another function, version 2, okay, F prime, let's call it, and it'll go through and replay everything and check to see, does it get the same answers? And if not, it'll tell you when it doesn't get the right answers. And how does it do this? It basically has to call eval, okay, with a different environment, because it has to reconstruct the global variables. So again, we have all these tools. Okay, you don't need to understand how to do it because it's hidden, but understand it's possible. So if you ever get yourself into a situation where you go, God, I really wish I could automate this, you pretty much can. Okay, okay, everyone happy? Where are we? Let me just. Okay, so we've now essentially, I've told you how to get the tests. We didn't do it, by the way. We're now about to gotta make this code fast, okay? There's another code repository where I actually built it excruciatingly painfully, okay? Where I actually went through and I redid all my changes in order, so you can actually go and check out different change points and see what you get. So, and how we collect these arguments is in there and so forth. So you can reconstruct these details. Okay, so we have these tests. Okay, blah blah blah. By the way, there's another little funky thing. Trace is really nice. Okay, just so you know, trace is nice because now slowly building up into how we're going to make this code better, faster. So again, what we've been talking about so far is we need to do this because we're working with somebody else's code or our own code, and somehow when we need a whole lot of software engineering approaches to actually do our job. We haven't even hit the code yet, but that's fine. But one of the problems is when I ran the trace, so I just loop over the 45 functions and call trace and set it up. Okay, and I'll show you the code if you care about it. But it's just building these language objects and whatever. Very simple. Not very simple. It builds on top of what we've seen today and nothing else. Okay, but the problem is then I ran it, took my 10 minutes. By the way, when you're doing this, when you're collecting up all these arguments, it takes a lot more time to run because it's doing extra work. So it didn't double it. But it can be bad. And if you do it wrong, if you just keep on appending to the last element of this global non-local variable, that's when it explodes because you have to pre-allocate them, okay, and then grow it. I mean, that's just a regular problem we have. So so that all gets taken care of in call counter. That's fine. But it turns out that all of my prep functions, the ones that are the workhorses, I know they're the workhorses, they were never called. Not a single call, which is odd because I know I can see in the script calls to at least 2 of them in a loop. So there has to be at least 2 calls, okay? And the reason is because this, f equals vectorize of g, let's say. Well, let's just take a look at what that does, actually. So I'm going to write this. This is a totally useless thing to do. Okay, but let's just do this, which is f is equal. G is equal to some function x, and we're just going to x plus 1 now. That is itself a vectorized function. If I pass in x as a vector, I get back a vector with 1 added to each element. So it's already done. Although people still do this, which is vectorize g. Okay, so let's just call that f. Okay, now f of 1 through 10. Okay, what's it going to do? It's going to do exactly what g would do. So this is a really stupid example. Okay, unfortunately, unfortunately, I have been using R and the S language for so long. I think in vectorized form, so I can't come up with a good example of when it's not vectorized, okay, off the top of my head, okay, and that's why when you're using R, you really want to think vectorization, so it's a good thing. So when I do this, I get the right answer. That's fine, but let's look at F. What the heck is that? It's kind of this is another meta programming thing. It just says, yeah, I can vectorize your function. I can vectorize any function. Okay, because I just do the same thing. What it actually arranges to do, and this pertains to 2 things, okay? I'm telling you this because it broke our tracing mechanism for catching the arguments and the number of calls, but it's also going to kill us in this code. This is going to be where it's going to be the second biggest problem we have with the toy script, okay? And that is basically what it does is it says, okay, where are we? So what it basically does is you give it a vector like this. So let's say it takes 2 arguments, okay? And this is just a scalar, let's say, and this is a vector. So, okay, what it does is it says, okay, we're going to call f with this thing, but what vectorize does is it says, sure, I'll take g and I'll arrange to call g with this guy and this guy as in one call, and then this guy and this guy again in another call, and then this guy and then this guy in another call. So it'll make, if there's 3 elements here, it'll make 3 calls to G. Yeah? Which is exactly what we don't want. We want vectorized calls. We want to call G with all of the values and have that be vectorized. But this makes it vectorized. So we can use it in a vectorized manner, which is nice. So it's going to slow us down a lot because essentially it's doing all scalar calls instead of vectorized calls. Okay? Everyone with me on that? If it's unclear, we can this is the heart of the matter. Okay, we need vectorized calls. Why we get the factor of 500 speed up is because we vectorized.
Just curious, if R is vectorized in nature, why do we have this function? Because
there are functions where it can't. For one, it makes it easier. Okay, there are certain times when you actually need to. One of the common cases is I forget is something like curve. Okay, to draw a curve. So you basically say, I want to draw this function between 0 and 1. Okay, and that needs a vectorized function. And if your function doesn't work, but it has to be called one element at a time, this works. Vectorized just makes it compatible with a function like curve. So it just says, yes, you have either been lazy and haven't written your function in a vectorized manner, or you can't. Okay. So we'll do it for you, and then it'll be compatible with the vectorized other functions that need the vectors in a single call. Okay, so it does work. There are certain things you can't vectorize. There are certain things you have to think really hard how to vectorize, and I'm going to show you one of them. Okay, but you got to think weird. There's the one thing I'm going to show you is you really have to twist your brain and think about it in an entirely different way to make it vectorized. So this is handy, and I was joking when I said you're being lazy. You got better things to do with your time. Just vectorize it for me, please. Yeah, I don't care about the speed until you do, and then you go, okay, Now I care. Now my priorities are different. The decision making is very different. One of the problems with this is let's trace G here. Okay, so we had F was made from G. Okay. Okay, so now let's just say trace G, and I told you. Okay, it's going to get called 10 times now. G is going to get called 10 times. So if I now say F of 1 through 10, it wasn't called at all. G was never called. And that is because when we look back at here, we've called vectorize with G. This is what we got back. See what it's calling? It's calling mapply to do the looping. And it calls this thing called fun, which is the argument into vectorize. Okay? See? That's the argument, that's fun. That's what it's now called. Okay? G was what we gave it in. It didn't care about the name. It grabbed the function object and it said, I'll keep that for later, and I'll squirrel it away. And when somebody calls the F, the vectorized function, it will call the object, the function object, not the name function G, but it'll call the function that it was given, okay? This is to do with scope, okay? So if I actually take a look at the environment of F, there it is. It's different than most things, but hey, there's the fun, okay? It's in there. That's what's going to get called. If I actually take a look at this, stop it. If I take a look at this guy here, that's G, but it's not called G. It is the thing that G was bound to. It's okay. It's G is a variable. This is the value. Okay, so that's going to get called. So anyone know how I can trace this guy? I need these arguments. I need to collect all the arguments. I need to know how they were called so I can test the functions. I can't have these 15 functions not be testable in my creative way of collecting all the calls. So because they're the guys who are doing all the work. Okay. So here's what I have to do. It's actually not too hard. Hey, let's just do this. Let's get again. B is equal to this guy. Trace B. Okay. And the environment of fun is equal to B. Okay. Now let's go back over to here. Come on, over there. Why didn't that work? Why did that not behave itself? Curious. This is what you do. Okay, let's not think about it. Okay, but basically what I'm going to do is but basically what we're going to do is we're going to actually go in and replace this function. Okay, we're going to take it, trace it, and then put it and then put it back into the function so it's available for us again. Why we didn't actually get to see it? Why we didn't? Curious. Here I should see calls to trace, and this behaves itself absolutely fine. I'll think about it momentarily as we go along. Okay. Anyway, so the point is you have to do some search on this. Again, it's not hard because we can find all the functions that are vectorized. You know, we could actually programmatically look at them and sort of say, hey, you seem to have a call to do.call mapply, and you've got this thing called fun. You must have come from a vectorized call, or we actually know which ones are called with vectorize. So we can go and identify those functions, and we go, okay, we got 15 functions we got to treat separately. Okay, and I say I have the code. I'll show you that it works if you care. Okay. So anyway, so that's it. So we need to actually we need to adapt this to collect all the calls. Now we're going to make this code fast, and I tell you that the mapply in these vectorize is going to be one of our biggest offenders. Okay, and if you actually look, so what do we do? Okay, so hopefully you've seen this before. Okay, there's a function called rprof, capital R, so rprof. Okay, and you basically just do something like you give a file temp, okay, whatever it is, temp.prof or whatever it is. You just turn this, you just call this function with the name of a file, and it does nothing. Not quite. It doesn't do much. It doesn't appear to do much. So we do this. What do I want to do? I don't want to run this code, okay? Because it just takes too long. So I have another version of it lying around, but which we possibly could use. So I do this. I do this, and now let's just do this. Let's do the following, which is replicate 1,000 times rnorm Okay, this guy, okay, and we'll take and compute the median of this guy. Okay, it won't take too long. Oh, I didn't want this. Okay, okay, didn't take very long. Okay, so now we say rprof null. Okay, so what are we doing here? Let's just kill off that guy. What am I doing? I turn on the profiler, I run my code, I turn off the profiler. Okay. So now it's stopped collecting information about how it's behaving. Okay, and now I do summary rprof of, I'll call p is equal to this guy of the name of the file I told it to use to collect all the information. Okay, so now I just do that again. So it goes and reads that file and collects the information in a weird way. You can take a look at that file if you want. Okay, it's not, this one's very short because I didn't want to run for very long, but it basically just samples what's happening in the engine, in the R engine every so often, and it prints out the call stack. Okay, this means that we were in the call to R norm that came from the call to replicate, that called sapply, that called lapply, that called fun, which is our fun, okay, and then call this guy, and then we saw the median was in here, so it can actually compute which function is taking how long. Okay, it's statistical. Okay, it's not 100% accurate, but it's perfectly good. I mean, it gives us everything we want, and we don't want to actually do it in a non-sampling way. Okay, so basically, what do? We say what I live by this. Okay, so P, and I look at the by self. Okay, so I read the thing back in. So turn on the profiler, run my code, turn off the profiler. Otherwise, it continues to mix in commands we're using now. Okay, and then I just read it, and I look at the by self, and I see, okay, what have we got? Our norm took 0.1 of a second. Okay, and it was 83% of the total runtime from when I was profiling. So if I wanted to speed this up, I would attack R norm. Don't even. Okay, but here this is so in the repository that I have. So code sandbox. So you can look in the Git repository. It's kind of a bit weird. Okay, I'll just help you if you do want to look at this. And it is actually, to me, this is a very, very nice example. I didn't know it was going to turn out to be as nice when I was doing it. I went through about 27 steps, okay, to make this code better. Okay, and I wrote and I detailed it in excruciating detail, as I say, 200 pages of random text. Okay, and I broke it into blocks, and then they're named. Okay, and I actually have and so in the Git repository, there's actually tags for particular commits corresponding to these 27 different stages, and you can check those guys out. Okay, and the order, there's fortunate enough you can actually ask for the tags in order, and you can see which ones. But I have a plot that I can share with you. But if we just take a look at this, this is I run this code. Okay, and this is not that I didn't want that. I wanted this one. Okay, so this is what happens. You run this code, it prints out a bunch of stuff. Okay, this is after I'd separated these functions out from the toy. This is what I ran. Okay, now we're ready to go on the toy. Okay, you get this output. This is what we need to faithfully reproduce. If we're just going to do the simple test of did I get the right answer for the one variable, that's what I need to recreate. Okay, anytime that doesn't look right, I'm in trouble. Okay, and then this. Okay, so I ran it twice to give it a slightly better timing. And then this here is the profiling output. Okay, this particular run took 601 seconds, so 10 minutes. Okay, okay, and this thing, by the way, tells us that there was 1 second, which is a very small proportion of it, but there's probably memory issues here. It's probably sort of stopping and clearing itself, okay, which is not our code running, it's R's internal engine that sort of says, I'm not going to count that against you. Okay, so that's fine. Okay, and then this is our profiling thing. It always prints in order. Right? This is this is by self, which I always look at, and this says 82 seconds. So not a whole lot of time, but more than 10%. Okay, 15% of it is attributable to the if-else function. Who knows about the if-else function? Okay, another one to take off your list. It's nearly always the wrong thing. Again, it's convenient. So and use it to your heart's content, but oh my God, does it do too much? Okay, I mean, you're just sort of saying, I want you, if it's this, do that. If it's that, if otherwise do that. Oh, and by the way, could you check for all the NAs and could you do a whole bunch of extra stuff that I didn't want you to do and didn't even know you were doing? And if I call it enough times, it's going to seriously become a bottleneck. And this is, so the way we profile is this. Okay, and hopefully this will all connect the dots. Now, I look at the profiling table. I will not go and try to make if else faster. That's in R. You can't. Okay, I mean, you can hack on R to your heart's content. We'll take patches back if you make it faster and it still works. You got to make it still work exactly the same. Okay, that's fine. So I don't hesitate to actually go and fix it if you think you can, but it's unlikely because a lot of eyes have seen it for 20 years, and you know there's probably a good reason for doing that. And also we can't fix mapply. None of these functions are ours. So great, our job is done. Okay, we can't make any of these faster. Well, the answer is we got to go find all the calls to if else and try to get rid of them. How do I find the calls to if else? By the way, if searching P. So again, programmatically we can. So in this case, it won't be P; it'll be the functions. Okay, and in fact, we don't have to parse now. We can actually just go and say, hey, we can use code tools again to find globals, saying, hey, which one of you uses find globals or uses if else? So we use find globals to find out which function has calls to if else, and we then go and attack those. Again, now there's only 45 functions, so it's not a big deal. You could actually do this in a text editor, but why? Yeah, okay, you probably should, but once you get bigger, it starts getting annoying to go find these things. But the real problem is you won't find mapply. There's no calls to mapply in our code. Why? Because vectorize created those functions. So when you go in with a text editor and you say, where's those? Nobody calls mapply. Okay, you could use trace or debug to actually stop when mapply is called and go, where am I? Okay, so you can sort of use that to find out where the calls are coming from. But the other way to do it is just to programmatically go through with code tools, find globals, which one uses mapply, 15 of them. How coincidental. Okay, they're all coming out of vectorize. So we're gonna want to fix that for the reasons I was talking about, because it just basically does a loop. Okay, and it doesn't actually get natural vectorization. It just forces it in a scalar, in a single variable at a time, value at a time. Let's take a look at the if else's. Let's go and take a look at toy. Okay, so how are we going to fix this? Let's go back over here. So actually, let's go. If you take a look at functions orig. Okay, I put in both repositories, there's a functions _ orig. So I lock those down because I need to be able to go back to those very quickly and test that I haven't broken them as well. Okay, so so where's the if else? So here's the first reference to if else. Okay, it turns out again, this code is just set up beautifully for teaching. Okay, because you're basically going, okay, this function, by the way, final inflow prep is only called once. Okay, well actually this one here is only called once. So it's really not worth fixing, but it shows exactly what's going on. What's the problem? Okay, so this is one. So this takes in a single value for month and a value Q. We don't know, okay. But it's the way we've set it up here. If nobody else calls final inflow prep, this is only going to get called with scalars, with a single scalar, a single value for one value for this, one value for this, as opposed to a vector. And then it just checks month. Okay. Okay. So one thing, is how do I get rid of the if else? It doesn't matter here because it's only getting called once. But can we learn from this? So think about that momentarily. I'm going to just go off and find another if else. Oh. Hey, there's another one in here. Nested if else's. That's another problem we have is there's a lot of calls to if else. The profiling, by the way, doesn't tell us how many calls there were. So we have to run that call counter thing separately, but it's very useful to say, great, that took 15% of the time and it was only called once. I really should fix it. Or it was called a bazillion times. I'm not gonna, even if I squeeze out a millisecond, it's not gonna make a difference. Okay. In might be a better choice. We want to think, we need to think. So we would like to vectorize this. It turns, yeah, so okay, we'd like to vectorize this. So we can use in, so month is in, but that would still just give us the logical value here. We'd still be using if else. Is this condition true? Okay. So this function is particularly easy, okay, to vectorize. So what are we trying to do? You got to be careful here. And I'm trying to vectorize, and I'm trying to get rid of if else. I should probably do one thing at a time, okay? Otherwise, my head will explode, and I will I will break these functions seriously badly. Okay? So maybe we just think about doing them one at a time, okay? And then that's when we could do it within. So for example, where are we? So, you know, let's just pull this guy out. Well, actually, let's just go down a little bit more. Okay, so, yeah. So there's a bunch of, now there's 4 if else's in there. Okay, let's just take a look at this guy here. Okay, because this shows something slightly different. Can you see this? It is hard to read. This is one of the things, it's hard to pick up other people's code, so it's nice to programmatically sort of do this thing. Anyway, how can I make that go faster for one? In two different ways. I'll use if, I'm going to get rid of the if else, but there's one immediate thing I can do to make this faster. Which bit? It's hard to tell. Not entirely hard to tell. Again, programmatically, you can tell this very simply. This expression here, all the way up to the ending parenthesis, is exactly the same thing as the third argument to if else. So what this is basically saying is, please, would you calculate this thing? So we could lift this out, do it once, and then take and assign it to temp, and then say, for if else temp is less than 0, give me 0, and then otherwise give me temp. Okay, and that's just avoiding doing repeated calculations. There's 2 reasons we want to avoid this. One is just wasting time computing the same thing twice. The other reason is it's going to make my code a lot simpler to read and to adjust. So I'm going to change this because I don't want to use this at all. But so the first step is avoid redundant computations, and that actually gets you quite a long way here. So one of the really nice things about this, let me show you this plot. So this is my plot. Okay, this is rare. You don't often get this. Okay, so this is what each of my 27 steps. Okay, this is the speed up a factor. Okay, the ratio of the runtime now at this step relative to the original runtime. Factor of 500. Okay, this is just great. Okay, really, really nice. This is minute. Okay, so I'm not getting any speed up here. I am. So I look at this. Now, this is the difference between each step, the runtime difference. So by making some simple changes, I'm getting a minute back. A minute out of 10 minutes makes me happy. By the time I get to here, so I've collected up, you know, a bunch of stuff. I can now run this in 2 minutes. And this is now I can start taking chances, if you will. I can start making small changes and see if they work. And it makes my life a lot simpler, because it's just, when you start running this and you know you can't do anything for 10 minutes and you don't know if it's going to work, you think a lot harder. Okay, so now we get very small changes, but as a percentage, it's huge. Okay, so this is seriously, but in this case where I have repeated computations, I got about 10 seconds back on this sort of stuff just by saying, you know, why are we doing this? But it cleaned up the code an awful lot, so I could actually then see things a lot more clearly. So yeah, so basically if I just take this guy, okay, so is everyone with me? You just take this expression, make it a temporary variable, okay, and then just use the result, okay? Now, so let's just lift this out, okay? Let's just take this guy. Okay, so I'm just gonna, okay. So let's just do this. So what are we talking about here? We're just doing this. Okay. Temp equals this guy. And now we're basically, oh, look at this. This is so much easier to read. Okay. Kill off that guy. I better be very careful that those really are the same expressions. And by the way, there's a lovely piece of code in here where I actually found 2 bugs. Okay. And you know, one we'll get to in a moment, and then the other one was where it was VW and V capital V capital W, and fortunately enough, there was enough idioms in other functions that says that looks like it's different from all the other ones. And again, programmatically doing that, I mean, I did it by eye, but you can programmatically do it. Because when you got thousands of lines of code, this is hard to actually get right. So you want to make sure. But again, we've got tests. We now collected all those results. When we make the change to this function, we're going to be able to run those tests again and see if we screwed up. So now this is, okay, I'll even do this. I hate removing comments, but let's just do it. There's one other thing, by the way, that's redundant here. Okay, so this is much cleaner to look at, in my opinion. Okay, and it's faster. Okay. Now, it doesn't make any difference. If this is a very simple calculation, it doesn't speed it up very much, but it still gives us the benefit of cleaner code. There's one other redundant computation in there.
You could just do the informal expression without assigning it to a just.
So actually what happens, R will say, oh, you want me to take the value and assign it to this thing. That takes time, people, okay? And now it looks ahead, now it evaluates this command and says, oh, I now need to go look this thing up, okay? I just had it in my hands a second ago. Why didn't I just give it to you? Okay. So, and also actually it is marginally faster not to call return, because the R automatically returns the last value of in the function call. So first of all, let's just get rid of the whole thing. Okay. Okay. Now it's very useful to actually assign this value if you're debugging and you want to go in and look at the end because it's disappeared. Okay. But that's a temporary thing. Okay. So I went through and manually removed all these things. And how did I do it? Again, I'm like a broken record because so few people do it. Because I have a little tool that goes in and looks at the body of a function and sees, is the last expression a call to return with a name, a variable name, and was that variable name the left-hand assignment of the previous expression? Easy to do with these language tools. And you go, oh God. And it saves you a little bit of time. But again, it makes your code cleaner. It's just, this is much easier. So tell me another way of doing this, because I need to, remember, my whole purpose here was to get rid of the if-else. I haven't gotten rid of the if-else. I got rid of the repeated computation. That's good. I've made my code cleaner, but I've still got the same number of if-else calls. You were going to say?
Just want the maximum of temp and 0.
I want the maximum of temp. So you can look at it. Now we have to, oh God, now we're actually reading the code. Oh, this is taking an ugly turn. Remember, I have not read the code until this point. We have not had a clue what it did. Okay. So, and that's the beauty of this thing. You can debug people's code and you can make people's code faster without understanding what it is actually trying to do. It helps if you understand what it's trying to do, but it's not obligatory. Okay. Yeah. So it's basically sort of saying, hey, compute this thing. And if it's less, and for any element that is less than 0, can you just put 0 in instead? So there's two ways to write that, okay? So we can, so we have this one, you know, so we could just do this, okay? We'll just do this. We could just do p max of temp and 0. P is parallel max, so it's an element by element, okay? And that's fine. Okay, so that's fine, and now we just, so we delta BC equals this guy. And by the way, hey, I could take this idea of removing the assignment here. Let's just put this inside here, and let's put that inside here. Okay. Okay. Now the code is unreadable. Okay. So just you've got to keep this code readable, because especially if you're doing it for someone else, are you going to share, collaborate with people? Oh, great! I made the code unreadable. I hope you don't mind. You know. So this is fine. So now actually I did this. Okay, I actually use this. It's expensive. Okay, I can do better than this. So how do I do better than this? Just bracket. I'm going to need a little bit more specificity than, can't you just bracket it?
Well, if you just assign a temporary variable and then whatever it is you're indexing to check temp, yeah, less than 0, and sign that, and then apply that. Yeah.
Yep. So that's actually faster, okay? Why? Because Pmax is doing too much, okay? Maybe. So I would start with Pmax. Pmax is absolutely fine. Where we're going to get ourselves into trouble is missing values, where we get where if else is actually handling missing values in a very specific way. So if it's got weird things going on, it will just create a missing value in the result, and we have to faithfully get the right answer. So we have to, sometimes we may actually have to check for NAs in here. That's going to slow us down, but so it may be faster, it may be slower, we don't know. But this is a very nice version. It turns out that it's slightly slower than this, so significantly enough. So after a bunch of profiling, Pmax will show up and I only had it in about 4 or 5 functions, and it's like, okay, that needs to go. How do I do it? I do this. And by the way, this is the trick to almost all of this stuff. Okay, so if we go back over to this guy here, let's pull this out. Anyone know how to make this guy go faster? Well, we can use the same sort of trick. Okay. Okay, so now we can, we'll just basically go. Well, so one of the things we can do is, so there's a couple of things going on here. You notice we got Q 1.98, Q 1.98, Q1. So what's actually going on here if you think about what's going on? First of all, we can just pull that out and apply it over here. Okay, so let's just, so again, how do we know this? This is very specific to one particular block of code. It's the thought process. You're profiling, you've got to get rid of the if-else's. You've got to try to avoid as much redundant computation. So we could just do this, 1.98, okay? 1.98, okay? And you know what I'm going to do, actually, just for fun? Let's get rid of this. So now what's this thing doing? Anyone know what this thing is doing? Yeah, so now we just look at this part. Okay, so what's this part doing?
Just the number of days in each month.
I know the number of days in each month. Actually, we didn't. It's wrong. Okay, because it's annoying. Okay, well, it's no, it's actually June and May were actually inverted here in terms. Okay, and that's just an error. It's just because it's tough. Okay, but how do I make this go faster? So first of all, I can actually, first of all, I can say month is in there, okay? But actually, there's, I'm doing something bold here. I've decided I'm trying to get rid of the if-else, but I'm going to vectorize at the same time. But I shouldn't do that. I really should just stick with one thing. But how could I vectorize this really easily without changing much of this? I could just cut out half the vertical bars. Just take one out, and I got to take the right ones, not just these 2. Okay. Okay. So I just, every time I see 2, I take 1 away, and because the single vertical bar is vectorized. So when I pass in a big long vector of months, it just takes the first one. Okay, and that's not what I want. That's a bug. Okay, but if I pass in a vector of months, but I make these a single vertical bar and this a vertical bar, now the whole thing is vectorized. Okay, I'm still doing, but of course I will still be doing too many computations with the if-else's. But that's one way. So a lot of people make a mistake with this stuff. When you want vectorization, you always want to be using the vertical bar, single vertical bar. Well, in many cases you actually want to say, if something is, if this and this. Remember what I was saying? If this is a call and the third argument is also a call, I need a double ampersand there, or a double or to say or, because it needs to come back to a single scalar value. If you say, this is always a problem speaking English, and if you say if and you pass in a vector, R will give you a warning and only use the first one, and it's always wrong. You nearly always want any here or all or something, but you can have 2 expressions here, and then you bring it with a single vertical bar. That's not what you want. You want 2 of them. It's this condition or that condition have to give you back a scalar. Okay, that's what the double ones work on. Okay, that's good not to know about them because you won't use them incorrectly. Okay, how do I get rid of the if? Yeah.
Just one more thing. When you use double bar, you want the 2 inputs to that conditional statement to be scalars, right?
Yes, this has, yeah, for the double ampersand or the double bar, vertical bar, the double pipe. Okay, you want them to be those to be scalars. Yes, the two arguments. You can't. Yes, they should be. Yep, and otherwise it'll warn. Okay, and it'll always use the first one. That's which is always wrong. Okay, so fine. So basically, what we want is we want to do this, and we want to just find the number of days in the month. How do we do this? Again, we can use if-else if we want, but we want to get rid of the if-else. That's what we want. Forget about the vectorization. I give you a month, and you give me back a number, which is the number of days. And we know what they are. But this is an awful long way of doing it compared to what the way we think about R. Anyone want to tell me how they would go about doing it? Just a name vector, not a list, but okay. Yeah, I just create a name vector and I just say, give me the element indexed by month, and we're done. And then we're out there. Oh, by the way, that's vectorized. So it's out of here. Okay, we've done both in one go. So yeah, basically what we do is we just basically say, so we say month, I have this somewhere else, month, what the heck is going on? Okay, month days or whatever we call it, you know, now we say, you know, January equals 31, okay, blah, 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 okay, we go there, okay, and now what we can just do is we can just say, get rid of this. Well, we can get, oh my God, we can just get rid of the whole thing. We just basically say times month, days, month. Yo, way cleaner, yes? And by the way, why did I do it here and not here? Pardon?
Only want to call it once, not every time it comes around.
Yeah, why am I creating this object multiple times? I can just go and get it. Okay, and because just for fun, okay, so this is much cleaner code. And it actually says what we're trying to do. Okay, it's way cleaner than the 2 if else's or whatever it is, the 2 or 3. Okay, oh, 12 o'clock, isn't it? You're here you're starting at 12, aren't you? Good, just checking. It wasn't 11:30. High times. So that's good. I'm going to show you one other trick here. Okay, and this actually gave me a good speed up. I forget how much I got. It's in that plot. And again, when I was writing this down, I sort of said, this is an extraordinarily aggressive approach, okay? And if I did it at the end, it wouldn't actually give me much speed up, but it shows you more about meta programming, okay? So by the way, I'm gonna clean this function up as much as I can here, okay? I'm gonna get rid of the curly braces. Technically, they actually add a minute extra thing, okay? So let me just do, I'll just do this, okay? So let me go over here and do this. Again, I'm trying to show you a concept. I'm not recommending you start doing this liberally everywhere, okay? I wanted speed. I needed to get this thing to run faster. So I started saying, how do I get it to go faster? And it wasn't I needed to go faster to actually speed up my process. Okay, I couldn't wait 10 minutes or whatever it is. So I have this function, okay, and I have months, days, okay? So we just got, so the trouble with this, it's no trouble at all. But this is such a minute little thing, but it's marginally interesting. When I put it outside here, so I didn't have an expression in here that had to get computed. You know, this is a constant. Okay, it never changes. Okay, so what do I do here? Okay, so I didn't want to recompute it every single time, but I am paying a price because R, when it tries to find it, it looks in the function call frame and can't find it, so then it has to go searching for it along the search path. Very, very small penalty for this, but it's a penalty nonetheless. There's another function, okay, QLOOKUP. That gets called, I forget, I think it gets called, I have the numbers here, it gets called 500,000 times. And it does something, the way I had it, it did a lot of lookup because of the number of times it was called. So a small savings in that lookup time would actually save me a bunch of time because of the number of calls it's accumulated over. So here's what I do. Let's look at the body of final inflow prep. There it is. Let's just do the following, okay? Actually, because I'm lazy, and you can see my thinking maybe, I'm gonna redefine this function to make my life easier. I'll even do it properly, okay? Okay, let's look at this. What's that guy? Okay, so now let's do this following. Let's look at number 2 here. What's that guy? Remember, these are just language objects. Remember I told you about these language objects earlier on? Okay, so that's that guy. And what I want, and I want number 2 is there. What's that? That is, what is it? Anyone know what the class of that is? So I've gone into the body, and I've just drilled down into the language object, okay? It's a name, it's a variable. When we call this function, it will say, oh, you're a name. I need to go look you up. So here's what I'm going to do. And this is weird. This is very, very weird. Okay, there's that guy. Why is that different? Because let me show you this. Oh God, what did I call it? Why did I use the full name? Okay, there it is. Now I do this. Now I do this. I've inserted the object directly in here. This is where I was saying you can transform this code. Okay, I can actually just say, well, it's constant, it never changes. Why am I looking it up every time? Just shove it straight in as an object. Because now when R tries to evaluate this, it just basically goes, oh, I already have the object here. Thank you. I know how to subset it. That's all that's going to be happening, because this is now the first argument to this square bracket. So what I've done is I've inlined the constant expression, okay, the actual current value of it's a bit weird. You basically say, so we see it. This is what I was showing you. That thing is month days, and then I just assign it to be month days. And you go like, why are you assigning it the same thing? And it's not. This is the value of month days. This is the name that will be looked up later on. Okay, I've never seen anyone do this before. Okay, it's very rare. Okay, and it's my brain that works this particular way. But we use it an awful lot in other languages where we just inline this thing called constant propagation, where we just push it all the way down because we know what the value is right now. But in R we don't tend to use it. But I actually got speed up here from this, so it was actually useful. Okay, but again, I'm connecting it to the. Hey, it's metaprogramming. You are able to transform the thing, not just query it, but you can actually transform it and modify the function and avoid the lookup. Okay, so we go through and we make all those changes to if else. Okay, and we got rid of the repeated computations. Okay, let me just remind me where we're going with this stuff. Let me just look in here. Okay. Remind me where we are going. So I have this very long list of all the changes I made. Okay, so yeah, let's do this other thing. Let's just go and take a look at this. Okay, let's go take a look at this one. Okay, so here's another one of these functions. Okay, now I'm going to defy you to actually figure out how to actually vectorize this one. Okay. What's even more fun is this. Okay, so let's take a look at this function. First of all, we're going to get rid of the return Q and the Q here. So we'll just do as numeric of Q prep. We could inline the whole thing. That's not much. It's this guy here. Look up Y, okay, which okay, blah blah blah. Okay, is equal to this. Okay, so how would we make that faster? Okay, I'm going to tell you a couple of things. And by the way, I'm jumping through this quickly. Okay, how did I get to this function? I'll tell you what the problem is. So I profiled it. I made all my changes to if else. Then I rerun the code. I profile. It's still mapply is my bane of my existence. I'm gonna have to think hard about that. Okay, about the mapplies. I need to get that right. So I kind of was lazy, and I was sort of just taking the cheap, easy ones without going out. I don't want to change 20 functions in one go. And that's the way to do it. It's just incrementally move, because who knows if you're going to get any speed out of it. But so I profile again, and you saw in my early profiles, there is a square bracket data frame. I showed you the profiling, I remember it, okay, but it said if else, mapply, and then about 3 or 4 later, it said square bracket data frame. Well, now we have to find out who is calling square bracket data frame. That's nobody's calling it explicitly, so we could trace this. You could actually go and trace and find out which calls were in effect, okay? And there's in the call counter package, there's a mechanism to do that, to capture the call stack for any call. So you can find out who's calling it. It's in here. Okay, lookup Y is a data frame. Okay, if you read the script, if you read the toy.r script, you'll see lookup Y getting constructed, and in there it's a data frame. It comes out of climate and blah 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 blah. Okay, what it actually is it's a data frame with 4 columns. Okay, and if you take a look at this function QLOOKUP and TALOOKUP, this one they look remarkably similar. If we were writing this ourselves, we should probably actually write these as one function and have them share the code, because they are remarkably similar. But this one looks at the fourth column, and this one looks at the 3rd column. Otherwise, they're the same. So what you actually have is, and these, by the way, this lookup Y is not a very bit long. It's got very few rows. It's got 10, 15 rows, okay? That's great, okay? Now, what are we doing here? Okay, this one's gonna be, so I'll admit, I went and I made these things super fast, vectorized, okay? And I was trying to squeeze out the last couple of seconds, and I was down to 1.2 seconds, okay? And I was trying to squeeze out a little bit more, and I'm going like, how do I do that? And I realized it turns out these are never called in a vectorized manner. They're only called with scalars. Even after I vectorize almost everything, they're still scalars, okay? And that's something that happens in the script. Month and p are actual scalar values. So I did it too aggressively. I don't think it was a mistake. I had no idea what was going on. I'm just looking at the information I'm collecting and going, these guys are getting killed. And if I can vectorize these other functions, then a vectorized version will be good. So how do we vectorize this? Okay. So first of all, well, before we vectorize, how do I get rid of the square bracket data frame and make it, because that's expensive. And if you don't know why it's expensive, that you shouldn't, okay? But it is very expensive because it's doing an awful lot of stuff with row names, okay, and comparing bunches of things and fixing the data frame back up again. So I don't want to actually treat it as a data frame. I want to actually I don't want the overhead like Pmax and if else with all the NAs. I don't want to pay the price when I don't have to, because what I'm doing here is I'm going in to look up y. Well, first of all, hang on a second. I'm looking up y 3 times. I look up y, okay? I'm actually looking it up. I'm going finding that variable 3 times. So I could do my little trick of inlining it straight away, okay? That's very aggressive, okay? But it's fine. It might speed things up, but it's the real trick is I shouldn't be using square bracket comma 1. I should just be using double square bracket 1 and double square bracket 4 and double square bracket 2. So in other words, let's take a look. Let's take a look at this guy, funds. Okay, we go down here. So first of all, we'll just get rid of this, clean this up, clean this up. So what if I just did this? Give me the third guy, looking at the wrong function. And then now get rid of that, okay? So, sorry, okay. Okay, now, and then if I change this guy and this guy, does that do the same thing? Because that's, by the way, the most important thing, okay? Because I'm now treating it like a list. So I'm just pulling out a vector and off I go, okay? And that is faster, okay? So square bracket dot data frame is not your friend.
So lists are faster than data frames
because of the row, because of row names and extra computations that it's doing to fix it back up again. And also dropping, because here I'm going in and sort of, just give me one vector and just pull the vector out. You know, when I use the other version, it has to know whether to drop the data frame and just give you back the vector, or are you actually getting back 2 columns? And so it does a lot of extra work. Okay, so that's faster, that's better. Can I do better? Now I want to vectorize. There's never any need for which. There's never a need for which. It's just an extra computation. Is the only time you use which is when you want to manually look and see what's going on, and then you take it out of your code, out of your production code. So definitely which is not necessary. Okay, so this is good. Okay, even better. So now we're going now, and this does say. By the way, you know, I could do my bizarre inlining here if I wanted to, but that's fine. And by the way, one thing you don't want to do is inline something huge. Like if you gigabytes of data going in, it should be a nice small little thing, because especially if you print it, and then you just see the whole thing going by on the screen. That's fine. So this works. How am I going to vectorize this? As I say, it turned out, and it took me a while to say, oh yeah, we don't need to vectorize that, but how would you vectorize it? Because as I say, the trick is to vectorize everything in R. So look up Y looks like this, okay? So we're looking at number 3. We grab this, and we're going to subset this guy out, where month is month. We match month into this vector. Okay, so we take month here, and we say which one does it match in this first column? So it might match this guy, and it might match that guy. Okay, this is for a scalar value of month. And then we do the same thing for P, and it might match this guy and this guy. So therefore, the only valid match is this one, and we grab this guy. So how do we vectorize that? In month and p. I want it to work for month and p. So I could give me a vector of months and a vector of p, the same length, okay? Now the trouble is, I match this guy into these two, but then this guy, so I can't use match because I'm gonna get the first match, okay? And I can't sort of say which one. I gotta do this one at a time, or pair at a time. Anyone got any ideas? This is a tricky one. And by the way, I'm gonna give you a hint. This is a small table. This is a small, I think it's about 15, I think it is. And you basically get back, it's almost like, I can't remember if it's not quite correct, but it's almost like for each pair of month and p unique values, there's an entry. Okay, so we're really looking up for this combination of month and p, give me the element in the third column. Okay, so it's just a lookup table. It's almost in the name, lookup y. Okay?
Can you join one of them, please?
How do you mean join them? Go. If I pay, so what I could do is, yeah, I could take these guys, okay? I could take these two in the lookup table. This is the master table, okay? And I could fuse them together. I could just paste them together. But so like take the value here and the value here and put a separator in between them, okay? Just anything, just make a string. And then and then in this call, I could just fuse month and p together over here and match them in. Bingo, I've got my job. Is that going to be fast?
No, the joining is probably going to be something.
So we got to paste them together, which is it's not very expensive, but it depends what we're going to do. So that is a very good way of doing it, but there's a better way of doing it. P is just their probabilities between 0 and 1, but there's only a few of them.
So you could make your row names, your months, and your columns P.
So why don't we just take this data structure and change it? So instead of doing this, why don't we just take this guy here, okay? And this is my month, and this is my values of P as indexed by here. We just literally repeat them, okay? Like, so we put them in here, okay? So there's only going to be, let's say there's 12 months, but there's actually, let's suppose there's 24 here. We'll only have 12 values here. Okay, but we're going to have combinations, okay? And we use the month name, and then we turn this is a probability, but we turn them into strings, column names. And now what we can do, and this is subtle. I mean, it's actually, it's just basic R, and yet it's a mind shift because we have to go from one data representation to a totally different one. So basically what we're saying is this, as you say, look up Y, okay? So we're going to basically make this as a table. And then we're just going to use month and P, okay? Because the months will correspond to the row names over here, okay? And the values here for P, yes? So we have to make this an as dot character. So I have this code, you can see it, we can go through it if you want, okay? Okay, so we have to turn that into a character. Month is already a character. It wasn't a character because it was read in as a factor. By actually turning that off, we actually sped up the code because we were constantly having to convert it to characters for no good reason. So that was another one of the steps that we took. Okay, so this one, does this work? Is this right? This is slightly mind-blowing, okay, because we don't see it that often. That's all. It's actually quite simple. That's not actually going to do what we wanted to do. Remember the month name, the days of the month? We had the month, it was a vectorized thing, and we just indexed into that vector. And so if we had January, March, we got back 4 elements corresponding to the elements, the named element in the month days. Okay, is that clear? So what we're going to do is we're going to take this guy. Okay, we're going to take this guy, and we're going to, you know, I think I can just run this code really, really fast, and I'll show it to you. Okay. Somebody had a hand up?
I just was going to ask you to run an example.
I'm going to try. I don't want to. Code review code. Now, hopefully, I'm going to be able to do this. Source functions.r. Now, this is the joy. I hope I've left this in the right position. Okay. Source.functions. There we go. and then source of toy.r, okay, toy2.r, okay. It thinks for a moment. There we go. That's the beauty of actually having optimized this code. Okay. Otherwise, if I ran that on the original code, it'd be 10 minutes, and no, I wouldn't be able to show it to you. Okay. Let's just take a look here. Oh, stop it. Okay. So let's look up y. Okay. There it is. Okay. So we have this object here. Okay. And so we want the Q in there. Okay. Now let me just go over to here and do. Okay. So we look up y. Okay, so here's where there's lookup y. Now I'm going to actually change this. Okay, here's what we're going to actually do. This is the code. Okay, so we're going to create a matrix of zeros. Okay, I'm going to use a matrix here. Sorry, I'll show this. Okay, okay. So what are we going to do? We're going to build a two-way table, okay, with the names are going to be the unique months and the unique values of P, okay? And then I am going to take each pair here, and I'm going to look up the corresponding row and column and stick that value into here. Okay, this is when I'm making this two-way table. Then I'm going to subset it later on in the function. So I'm going to basically all these values, and I'm going to lay them out in a particular way that respects the particular value of month and the particular value of P. Okay? And then there's a magic little trick here. And that's why I was saying that what I was showing you was not quite right. So basically I just say, give me the unique values. Okay, create the matrix. And now I have to stick the values into the right place. And this takes my matrix or a data frame or whatever it is, but a matrix is what we normally think of here. And it's just going to take the values of Q and put them in the corresponding places. But if I don't have that C-bind, this is entirely wrong. Okay? Because what I'm doing is I am subsetting, or assigning in this case, but it's still subsetting. I have this matrix, and I am subsetting it with a 2-column matrix. Okay, so if I do it like this, where if I just do this guy here, M square bracket month and P, that goes in and grabs all the months, the rows corresponding to month, and then on the other side on the columns, it just pulls out the P's. Whereas I actually want the cells, not the columns and the rows. I actually want the individual cells, and this is how R does it. You use a 2-column matrix. Okay. And that says, oh, I get it. I go through this 2-column vector, this thing. I take this guy, and I find the corresponding row and column, and I give you that's the cell for that. Then I go on to the next guy. R does this in C code, so it's super fast. Okay, but that's how we do it. So this is a big shift. We've taken a data frame that's unraveled, and we turn it into a two-way table, and then we look it up using this 2-column subsetting operation. Okay, it's a bit weird because most people don't know about this because you don't use it very often. But when you use it, it's super fast. Okay. Kid you not. One of the places where, so after you do this and you're getting down, I've exhausted all possible avenues of how to actually make this thing go faster. C-bind was causing me a bunch of grief. You can't fix C-bind. Oh, you can fix C-bind. I didn't get much speed up out of it, but the trouble is C-bind will bind this column and this column and this column and this column. I've got 2 columns. I only need 2 columns, and they're character vectors. You're too general for me. So I actually went off and wrote a tiny little piece of C code to get a bit of speed up. Gave me a little bit, you know. So then it's fine. Then you're trying to reduce the number of calls to C-bind. Can you do this a different way? And maybe you can. Okay. So this is all good so far. Okay. So as I say, we're just driven by profiling here. Each time we run this, we profile it. Each time we run it, we check the result, okay? Check it's correct. We just compare best with best, okay? And then off we go, okay? And once that's true, then life is good, okay? We fix up we try to fix up these. Remember, we can find all of these guys. It is funny that in there's 15 vectorized calls. I counted the number of for each call, I checked the length of the arguments. There are several vectorized functions that were called only with scalars. So we're going through the extra layer of a vectorized call to do what we could have done by calling the prep function directly. So that's just like, okay, you know, we think we're vectorizing, but we're not actually doing that, okay? So that's fine, okay? So what else have we got? Pmax and stuff like that. Okay, so we do lookups for lots of different things. The if-else's, we also use switch calls because it's just, we're switching on a month, because month is a scalar. And throughout this entire thing, it turns out that month is always going to be just a single value. Okay, so we tidy up all of these guys. So we're running out of time, but so we get rid of the subset data frame that I talked about just with by actually using as a list. Okay, one of the big problems. This is our guy. Choose solve is the one who's getting called. Now it turns out, okay, and again, I need to know where it's getting called. How many places in the code are calling choose solve? Turns out 2. And again, I programmatically find this. They're in. Let's just go over and find those actually. I'll get back to something else in a moment. But if we look at accumulate, so there, that's it. This is going to be the magic trick. And if you can spot this early, this is good. You basically say, we can vectorize all of these other functions, but if choose solve is the only entry point to calling those other functions, they're still going to get called as scalars. But the nice thing is we can go this slowly, just not breaking things, get them all ready to be vectorized, and then make the last switch. And then we just pull this guy out of the loop and off we go. But while we're in this loop, let's just take a look at this one. This is a great one. This is a 2 nested loops. Okay, this one is only 1 nested loop. So let's learn from this one. Okay. Loop over this guy, call the choose solve. Okay. If else, this guy. Okay, that's fine. Then basically, if it's less than 0, I want -999. Okay, otherwise, okay, v states equals this guy and vw states equals that guy. This is looking like that 2-dimensional. Is it? Yeah, there's an ampersand here. That's looking like my 2-way table. See, that's why I told you about the 2-way table. It doesn't work here. Dang. Okay, it's okay. Maybe we could make it work. I'm not sure we care enough. Okay. Maybe we can. I think the answer is it doesn't. Okay, so we're slightly misled there, but there's not a lot of repetition here. Okay, we don't seem to be able to make this a lot better, but we should get rid of the if else. Okay, because we can definitely say, look, calculate this. So this is a scalar. So this is an if else where it's not even vectorized. This is really just, let's assume it's -999, and if it's not, we just do a regular if, then else. Okay, so that's fine. And we set FSJ to be there. And then if that guy is missing, okay, then it's this, and then if that, and so, okay, oh God. Okay, we never use FS later on. Okay, so why do we just get rid of the intermediate value and just check what's going on in here. Okay, so we're going to lift that guy out. Okay, we're going to pull this guy out and everything's going to change. Okay, so what happens when I lift it out? So I lift choose solve out, and now I got like a vector. So it should be the same length as RDEX. And I still need to loop because I can't vectorize this. What am I going to do? I think you may have mentioned this. Well, no, I think you mentioned it earlier. Very, very early, 2.5 hours ago. And that's the problem. You sort of forget your tricks because you're losing track. If we go back up here, this is an even more obvious exam. Nope, toy2.r. If we go back, if we go here, where are we going? Where are we going? Oh, well, nope, I can't do that because this is the actual version of the code. I need to, which one is this? Yeah, I need the other one. I need the original. Sorry. Oh, where to go? Sorry. This looks not, oh, that's why. Sorry, that's why. I keep looking at the wrong one because, so let's look at this, for example. We loop over Rdex, okay? Then we have a loop from 1 to 1. Seems unnecessary. Then we do this if thing again. This is all vectorized, so the if else should be just if then else or whatever it is. We probably don't need much of this. This seems to be identical, doesn't it? So again, we shouldn't repeat code here. But where am I going to get the real savings here? You don't know this. You can't know definitely, but it's a good guess. And I loop over all the values, and basically, if the corresponding V and R, I look in this matrix, if that's missing, then okay, if it's missing, then I get missing for the answer. If it's not missing, I go off and look at this guy. So basically what I'm getting is, if you think about it this way, by default, it's just, well, you know, one answer is it's just missing. And I only look at the values for which this is not the case. So if I change the loop to be over just that subset, if it will not help at all if all of them are missing, okay? Or sorry, if they're not, sorry, it won't help at all if none of them are missing, okay? But I can check this, okay? And it turns out that I think we're looking at less than 1% are not missing. So this is a huge saving, okay? So I can't reconstruct this loop. It's very hard to get this out. We possibly could do something with the two-way table lookup, but the simple thing is just to loop over different things, okay? And now if you look at this code, I think it is okay. This one's a little trickier.
For the general principle for that last one, if you're looping over something that only applies to a very small subset of your data, you're wasting computation.
You are, because you're doing it for every element when you should actually be just vectorizing the test to see which ones you should be looping over and then just looping over those guys. Yeah. So you basically just say, which ones should I look at? Do that fast. You know, you compute that logical vector fast, and then you go, okay, I'm only going to look at you guys. Okay. And I'd say we could probably do, now here, this is slightly this is slightly different. Okay. It's the same in some, it's almost exactly the same code. This is why the other one had one to length of 1, was because it's just cut and pasted code, which is great. Okay. But don't do that, because then we have to fix it in 2 places. But the trouble with this is, how do I find out which ones are, is this true? That they're not NAs in here. Pardon? Sorry?
Trying to figure out which ones aren't NAs?
Yeah, because I want to basically, what I'm going to do is I'm going to pull this out and I'm going to say, tell me which cells are not NAs.
Is like which.NA.
Hang on, we said which, there was never had it, never. No, we're going to need which. We're going to need the which, okay? I mean, you're going to need, so you can get away without using the which, but it's not worth it because you have to think. But basically, we have a matrix that looks like this. So if you just sort of say is.NA on this matrix, what you get back is a matrix with each cell saying true or false, okay? We need to find the trues, the falses in this particular case. We need to find those, and then I'm going to loop over them, okay? But I don't want to loop over all the cells in this thing, because that's what I'm doing over here. So what I actually want to do is I want to say which. So how many of you knew about this one? Which in is.NA and true. What's the name of the second argument? To which? Has ever, array ARR, yeah, array index. What it basically says, if you say false, it just gives you back a big long vector, because this is just a matrix is a vector, okay? So it's just column-wise ordered. So we could always figure out what that should be. But what this does is it gives you back a 2-column matrix with the rows and the column numbers for each cell. That was actually true, okay? And that's where we can just loop over that. So if this thing here is, if this is 100 by 100 and we've got 10,000, and if this is only 100 because it's 10% or 1% or whatever it is, so now we can just loop over these guys and then just still do the scalar computations in here, and life is good. But so we needed to actually do this. Now, can you actually, you can do that subsetting trick again with the 2 columns. So we might be able to vectorize this, but nah, it's going to be hard. And the other thing, what you can actually do is you can't really vectorize this, but you can vectorize, well, is it somewhere else where we actually call the function, where you call the function with all of those arguments and then loop over the results. So you're trying to always move back into vectorized stuff. Okay, so this, so we're running out of time. But as I say, if you want, so one of the things I actually did between the 2 repositories, the HydroSim one contains everything I did. Okay, and carefully committed, so you can actually go back and look at them. But I actually wrote a shell script and some R and a little R script to basically check each tag out and run it. Okay, so that you can do this programmatically and verify that you're actually getting the same answers and that you get what the speed you're actually getting is. So that's kind of fun. But again, it's just combining a bunch of tools. If you look in this file called changes by XML file, it's done in order. It hopefully describes all the high level steps that you might think about doing. There's lots of them. Let's say at one point I got into writing C code, which really was a waste of time. It was only because I was actually trying to teach with this thing rather than actually I would never do it in real life to get, a second or 2 back, not even that. Okay, so but I mean, so there's lots more to talk about this stuff, but hopefully this is useful. I was saying there's a bunch of packages that actually try to do a lot of the language processing for you. They are all on GitHub. There's a link on the slides. The link to all the packages are there. They're under mine and other people's. Yeah, and if you have any suggestions, but it's not for the faint of heart. This is not something I expect you to. Okay, now I know all about meta programming, and I think this is what I will do for the rest of my life. Okay, but the static analysis and the runtime with trace and other things is just so powerful. And this is a thing called code instrumentation. So you can just basically instrument your code to collect things that might be useful or of interest, and they kind of work, but very few people know about them, which is a shame. Anyway, so but if you want to, I think this is a really nice example of going through and actually seeing what worked and why. Okay, and if you're interested in reading what is currently 200 pages, I explain my reasoning. That's why it's 200 pages. But if you want, I'm happy to share it with you. So 3 hours is probably better than 200 pages. Anyway, and we'll have I'll be doing these three connected workshops on R fundamentals if you're interested in trying to understand how to reason about it. Let's say this is backwards. Here's how to make it faster. I don't know how it works. So how can I make it go faster? Anyway, thanks.